ASE Certification Test. Introduction to ASE Certification. Course Overview. The ASE Certification Test is a critical step for automotive professionals who wish to demonstrate their skills and expertise in the field. This course will introduce you to the ASE certification, its importance in the automotive industry, and the numerous benefits it offers for career advancement. You will also learn about the certification process and how to begin your journey toward becoming an ASE certified technician. Understanding ASE and its role in the automotive industry. The Automotive Service Excellence (ASE) certification is a globally recognized credential in the automotive repair industry. ASE certification verifies that an automotive technician has met the industry's highest standards in terms of knowledge and experience. What is ASE? ASE is a non-profit organization that has been certifying automotive professionals since 1972. The ASE provides an industry standard for automotive service and repair, helping employers and consumers identify qualified technicians. ASE certification is recognized nationally and is often required or preferred by employers in the automotive industry. Why is ASE certification important? Trust and credibility. ASE certified technicians are recognized for their expertise and can earn the trust of employers, customers, and colleagues. Industry standards. ASE sets the standard for excellence in the automotive field, ensuring that certified professionals meet high-level competencies in areas such as diagnostics, repair, and customer service. Consumer confidence. Customers trust ASE certified technicians because they know these professionals have undergone rigorous testing and meet high standards in the automotive industry. Types of ASE certifications. ASE certification is offered in a variety of specializations, such as automobile and light truck, the most common certification for technicians who work on cars and trucks. Diesel engines, for technicians who work with diesel-powered vehicles and machinery. Brakes, a certification for those specializing in brake system repair and maintenance. Electrical systems, focuses on diagnosing and repairing electrical issues in vehicles. Benefits of earning ASE certification for career advancement. Achieving ASE certification offers a wide range of benefits for automotive technicians, including greater job opportunities, higher earning potential, and the satisfaction of being recognized as an expert in the field. Career benefits. Increased job opportunities. ASE certification is often a requirement for many jobs in the automotive industry. Employers prefer to hire certified technicians because they are assured of a technician's skills and knowledge. Higher earning potential. ASE certified technicians tend to earn higher wages than non-certified technicians. Certification demonstrates expertise and may open the door to better paying positions. Job security. With certification, technicians are less likely to be laid off or underemployed because their qualifications are recognized by top employers. The certification assures employers that technicians have the knowledge needed to perform high-quality work. Professional recognition. Earning ASE certification demonstrates your commitment to your profession and enhances your credibility in the workplace. Customers and employers recognize ASE certification as a sign of a highly qualified professional. Opportunities for career growth. ASE certification can serve as a stepping stone to more advanced roles within the automotive industry, such as a service manager or shop foreman. It can also lead to more specialized areas of expertise, opening up new career paths. Personal satisfaction. Earning ASE certification also brings personal pride. Achieving a high level of skill and knowledge and being recognized for it fosters professional growth and job satisfaction. Overview of the ASE certification process. The process of obtaining ASE certification involves a combination of experience and passing the relevant exams. Here's how it works. Step 1. Meet the experience requirements. Before taking an ASE exam, you must have relevant work experience. The required amount of experience depends on the specific certification area. 2 years of work experience is typically required for most ASE certifications. Educational waivers may apply if you have formal training or coursework related to automotive technology. Step 2. Choose the right certification. ASE offers a variety of certifications across different areas of expertise. You'll need to choose the certification exams that align with your career goals and areas of specialization. Step 3. Prepare for the exam. Preparation is key. ASE offers study guides and practice tests for each certification exam. These materials can help you understand the types of questions that will be asked and the knowledge areas you need to focus on. Step 4. Take the ASE exam. Computer-based testing. Most ASE exams are computer-based and are administered at designated Pearson VUE test centers. Passing the exam. Each exam consists of multiple-choice questions based on real-world automotive scenarios. The passing score is typically around 70%. This varies depending on the exam. Step 5. Maintain your certification. ASE certifications are valid for 5 years. To maintain your certification, you'll need to renew your certification. ASE encourages continuing education and knowledge updating. You can recertify by taking the exams again or fulfilling continuing education requirements. Step 6. Receive your certification. Once you pass your exam, you'll receive your ASE certification. Your certification is valid for 5 years, after which you must recertify to maintain your status as an ASE certified technician. Conclusion and recap. In this lesson, we've explored what ASE certification is, its role in the automotive industry, and the benefits it offers for career advancement. We also provided an overview of the certification process, including the requirements for experience, the steps to obtain certification, and how to maintain it. Becoming an ASE certified technician is a valuable credential that opens doors for career growth, higher earning potential, and job security. The ASE Certification Test Format. The ASE Certification Test is an essential step in becoming a certified automotive professional. Understanding the test format is critical to preparing effectively. In this lesson, we will explore the number of questions, time limits, types of questions, and the different certifications available. This lesson will provide you with an overview of the test structure, helping you know exactly what to expect when you sit for the exam. Number of questions and time limits. The ASE certification test is designed to evaluate your knowledge and skills as an automotive professional. Here's what you can expect in terms of questions and time limits. For number of questions, the test consists of multiple-choice questions, with the total number depending on the specific certification exam. Standard exams typically contain 40 to 60 questions. Specialized exams may contain a higher number of questions, typically around 50 to 70 questions. For time limits, each test is timed and you must complete the exam within the given time limit. The typical time limit is 1 hour to 1.5 hours depending on the exam. It's important to pace yourself to ensure you have enough time to answer all the questions. Tip: try to spend about 1 minute per question, allowing extra time to review your answers at the end. Here's a breakdown of time. Multiple choice questions. These make up the majority of the exam, and you'll be required to choose the correct answer from several options. Time allocation. Typically 1 minute per question. Scenario-based questions. These questions present real-world situations, requiring you to apply your knowledge to solve problems. Time allocation. Scenario-based questions might require more thought and could take slightly longer, so manage your time wisely. Types of questions. The ASE certification test primarily includes 2 types of questions, multiple choice and scenario-based. For multiple choice questions, format. Each question will present a problem, followed by a list of possible answers. You will be required to choose the best possible answer based on your knowledge and experience. Example: what is the first step in diagnosing an engine that is misfiring? A. Checking for vacuum leaks. B. Inspecting the spark plugs. C. Testing the fuel injectors. D. Scanning for trouble codes. Strategy: eliminate obvious wrong answers. If a few answers clearly don't match the scenario, cross them off. Focus on keywords. Pay attention to words like first, best, or most likely, which often appear in multiple-choice questions to guide your response. For scenario-based questions, format. These questions present a real-world situation or problem, often with additional details or context, and ask you to select the most appropriate response or solution. Example: you are a technician at a repair shop. A customer brings in a car that won't start. After testing the battery, you find it is fully charged. What should be your next step? A. Check for fuel system issues. B. Test the starter motor. C. Inspect the spark plugs. D. Test the alternator. Strategy. Read carefully. Scenario-based questions require you to understand the full context and use logical reasoning to choose the best course of action. Use elimination. Similar to multiple-choice questions, you can often eliminate certain options that don't apply to the situation. Test-taking tip. For both types of questions, always read the question and the options thoroughly before answering. Don't rush to select an answer based on an initial assumption. Different ASE certifications available. ASE offers a wide variety of certification exams, each focusing on a different aspect of automotive service. Below are the primary ASE certification categories. A-Series certifications. These certifications cover various general automotive repair areas. L-Series certifications. This is an advanced certification for those with extensive experience in engine diagnostics and repair. C-Series certifications. This is designed for technicians who specialize in maintaining and repairing light vehicles. And other ASE certifications. How to choose the right certification. Depending on your career goals, you may choose a general certification like A1, A9, or focus on a specific area such as diesel engines or advanced diagnostics. Each certification will require different levels of experience and expertise. Practice questions for review. Let's review some sample questions to familiarize you with the test format. Sample question 1. What is the first step in diagnosing an engine that is overheating? A. Check the coolant level. B. Test the thermostat. C. Inspect the radiator fan. D. Replace the water pump. Answer: A. Check the coolant level. Checking the coolant level is typically the first step in diagnosing an overheating engine. Sample question 2. You're working on a customer's car, and they report that the car pulls to the left when braking. What should you check first? A. The brake fluid level. B. The brake pads for wear. C. The tire pressure. D. The wheel alignment. Answer: B. The brake pads for wear. Uneven brake pad wear is a common cause of pulling to one side when braking. Test-taking strategies for success. To perform well on the ASE certification test, here are some strategies to keep in mind. Practice. Familiarize yourself with the test format by taking practice exams. This will help you get used to the types of questions and time limits. Read carefully. Whether it's a multiple-choice or scenario-based question, take your time to read and understand the entire question before answering. Pace yourself. Keep an eye on the time during the test. If you're stuck on a question, move on and come back to it later if you have time. Conclusion and recap. In this lesson, we reviewed the structure and format of the ASE certification test, including the number of questions, time limits, and types of questions you'll encounter. We also explored the different ASE certifications available and how to choose the right one for your career goals. By familiarizing yourself with the test format and practicing with sample questions, you can approach the exam confidently and prepared for success. How the ASE certification test is scored. Understanding how the ASE certification test is scored is essential for properly interpreting your results and knowing what to focus on for improvement. This lesson will guide you through the scoring process, help you understand what constitutes a passing score, and explain how to interpret your score report. By the end of this lesson, you will feel confident in understanding your performance and how it impacts your career advancement. Understanding the passing score and requirements for certification. The ASE certification test is designed to assess the knowledge and skills of automotive professionals. Understanding the passing score and certification requirements is crucial to determining whether you have achieved the certification and what areas may need improvement. The passing score for the ASE certification exam typically ranges between 70 to 75%, depending on the specific test you are taking. Example: if the test consists of 50 questions, you may need to correctly answer 35 to 38 questions to pass. Standardized scoring system. ASE uses a scaled scoring system to ensure fairness across different test versions. This means that the number of correct answers required to pass may vary slightly between test forms, but the overall difficulty is adjusted to maintain consistency in results. How scores are calculated. Your score is based on the number of correct answers out of the total questions in the exam. Each question is worth 1 point. No negative marking exists for incorrect answers, so it's always better to make an educated guess if you're unsure about an answer. Certification requirements. To earn ASE certification, you need to pass the relevant exams for the desired certification. For example, A Series, A1, A9. These exams focus on general automotive repair and specific areas such as brakes, suspension, and engine performance. L Series, L1, the Advanced Engine Performance Specialist certification, requires passing the L1 exam. C Series, C1, the Maintenance and Light Repair (MLR) certification, covers the basics of maintaining and repairing light vehicles. In addition to passing the exam, you must meet the work experience requirement for each certification. Typically, 2 years of work experience in the automotive field is required, though this can vary depending on your level of education or formal training. How to interpret your score report. Once you complete the ASE certification test, you will receive a score report detailing your performance. It's important to understand what this report means so you can accurately assess your strengths and areas for improvement. Here are the components of a score report. Overall score. This will indicate your total score on the test and whether you have passed or failed. The report will display your scaled score and let you know if you met the required passing mark. Example: if the passing score for a test is 70% and you scored 72%, the report will indicate that you passed. Individual section scores. Some ASE exams are divided into different content areas. Your score report will show how you performed in each area, giving you a breakdown of your strengths and weaknesses. Example: if you score high in brake systems but low in suspension and steering, it indicates which areas need more attention for future preparation or recertification. Performance categories. Your score report may also categorize your performance in different skill levels. For example, above target. This means you performed well above the expected level. At target, this means your performance meets the standard expected for that content area. Below target. This means your performance is below the expected standard, indicating that further study may be necessary. What to do if you don't pass. If you don't achieve a passing score, don't be discouraged. Use the score report to identify which content areas were difficult and focus your study efforts on improving in those areas. Consider taking practice exams or attending workshops to reinforce your knowledge. Here's an example of a score report breakdown. The engine repair A1 section shows that the candidate performed well, meeting the standard. The suspension and steering section shows the need for improvement as the score is below the target level. The brakes A5 section indicates excellent performance, exceeding the target score. Practice questions for review. Here are some sample questions to help you better understand how the ASE exam is scored. These questions are designed to help you practice and reinforce your understanding of ASE topics. Sample question 1. What is the purpose of a timing belt in an engine? A. To regulate the airflow into the engine. B. To synchronize the engine's camshaft and crankshaft rotation. C. To reduce engine vibrations. D. To monitor engine temperature. Answer: B. To synchronize the engine's camshaft and crankshaft rotation. The timing belt is responsible for ensuring that the camshaft and crankshaft rotate in sync, which is essential for proper engine function. Sample question 2. Which of the following is the correct tool used for testing battery voltage? A. Pressure gauge. B. Multimeter. C. Torque wrench. D. Spark plug tester. Answer: B. Multimeter. A multimeter is the correct tool used to measure battery voltage and other electrical measurements in automotive systems. Final tips for interpreting your score report. Review your weak areas. Your score report will help you identify areas where you need more study. Focus on the sections where you performed below target and improve your understanding in those topics. Use the results to plan next steps. If you didn't pass, use your score report to guide your preparation for the next test attempt. Make sure to review the content areas thoroughly and consider attending additional training if needed. Celebrate your success. If you pass, congratulations. Celebrate your achievement, but also make a plan for maintaining your certification and continuing to improve your skills. Conclusion and recap. In this lesson, we've discussed how the ASE certification test is scored, including how to interpret your score report and understand the passing requirements. We also explored how the results can guide your future preparation, whether you pass or need to retake the test. Understanding your score and taking appropriate action based on it is an essential part of the certification process. Preparing for success. Preparing for the ASE certification test requires a combination of strategic studying, time management, and using the right resources. In this lesson, we will discuss essential study tips, how to set realistic goals, and time management techniques to ensure you are on track for success. Study tips for ASE test preparation. Successful preparation for the ASE certification test relies on well-planned study sessions and active learning techniques. Here are key study tips to help you make the most of your study time. Create a study plan. Assess your current knowledge. Identify areas where you feel confident and areas where you need improvement. Focus your efforts on weak areas. Break down the material. Divide the study material into manageable sections. Plan to cover one section per study session to avoid feeling overwhelmed. Study plan example. Week 1. Focus on engine repair. Read chapter material and take practice quizzes. Week 2. Study suspension and steering and complete practice questions. Week 3. Review electrical systems and take a full-length practice test. Active learning. Summarize key concepts. After reading a chapter or completing a practice question, summarize what you've learned in your own words. This reinforces retention. Teach the material. Explaining complex topics to someone else, or even teaching an imaginary audience, will help reinforce your understanding. Focus on understanding, not memorizing. While memorization can help with definitions and formulas, understanding how and why things work is crucial in applying your knowledge during the exam. Practice problem solving. In addition to reviewing facts, practice solving problems, especially in the areas of diagnostic skills, repair techniques, and troubleshooting. Use spaced repetition. Review periodically. Spaced repetition involves reviewing material at increasing intervals. This method improves long-term retention. Time management and setting realistic study goals. Time management is crucial to ensure that you cover all the material effectively without overwhelming yourself. Setting realistic study goals allows you to stay focused and motivated throughout the preparation process. Setting specific, measurable goals. Set daily and weekly goals that are achievable. For example, daily goal: I will complete 30 questions on electrical systems and review my mistakes. Weekly goal: I will finish studying for the A6 electrical systems and take a 50-question practice test by Friday. Make your goals actionable. Focus on what you can do, such as completing a chapter or a set of practice questions, rather than vague goals like study for 2 hours. Prioritize your study time. High-yield areas. Focus on content areas that are heavily weighted on the test or that you find most challenging. Review progress regularly. At the end of each week, Assess what you've accomplished. Adjust your study plan if necessary to cover any remaining gaps. Break study sessions into manageable blocks. Pomodoro technique. Study in focused 25-minute blocks followed by a 5-minute break. After completing 4 sessions, take a longer break, 15-30 minutes. This prevents burnout and helps maintain concentration and productivity during study sessions. Build in buffer time. Set aside extra time to review challenging topics. Don't wait until the last minute to tackle difficult content. Practice exercises. Here are some practice questions to reinforce what you've learned about ASE test preparation strategies. Exercise 1. Time management question. You have 2 hours to study today. How should you divide your time to review for the engine performance, A8 and brakes, A5 exams? A. Spend 30 minutes on A8, 30 minutes on A5, then repeat. B. Spend 1 hour on A8 and 1 hour on A5. C. Focus on A5 for the first hour, then A8 for the next hour. D. Spend 15 minutes on both and then take a 30-minute break. Answer. C. Focus on A5 for the first hour, then A8 for the next hour. This ensures balanced coverage of both topics and allows for deep focus on each. Exercise 2. Setting study goals. Create a realistic study goal for your next study session. Answer. I will review 3 chapters on engine diagnostics, answer 20 practice questions, and identify at least 5 key concepts that I struggle with. Conclusion and recap. In this lesson, we've explored effective study tips, time management techniques, and recommended resources to help you prepare successfully for the ASE Certification test. By creating a study plan, setting realistic goals, and using the right tools, you'll be well prepared to achieve success. Engine Fundamentals. The Engine Fundamentals section of the ASE Certification test focuses on evaluating your knowledge of automotive engine systems, components, and designs. This lesson will provide an in-depth understanding of the essential components of an engine and how they function together to power a vehicle. We will also explore the different types of engine designs, such as inline, V-type, and flat engines, and discuss how these designs affect performance and vehicle application. Understanding engine components and systems. Automotive engines are complex systems made up of various components that work together to convert fuel into power. Understanding these components is crucial for diagnosing engine problems and maintaining engine performance. Key engine components. Cylinder block. The cylinder block forms the foundation of the engine, housing the cylinders and supporting various engine components, such as the pistons, crankshaft, and camshaft. Pistons. Pistons are cylindrical components that move up and down within the cylinders. They play a key role in compressing the air-fuel mixture and transferring force to the crankshaft during combustion. Crankshaft. The crankshaft converts the up and down motion of the pistons into rotational motion, which is then transmitted to the wheels through the drivetrain. Camshaft. The camshaft controls the opening and closing of the intake and exhaust valves, which regulate the flow of air and exhaust gases in and out of the engine. Valves. The intake and exhaust valves allow air and fuel to enter the combustion chamber and exhaust gases to exit. They are operated by the camshaft and are critical for efficient engine performance. Connecting rods. Connecting rods link the pistons to the crankshaft, transferring the energy generated by the combustion process to the crankshaft. Timing belts chain. The timing belt or chain synchronizes the movement of the crankshaft and camshaft to ensure the proper timing of the opening and closing of the valves. Cylinder head. The cylinder head contains the intake and exhaust valves, the camshaft, and the combustion chambers. It is bolted to the top of the cylinder block. Oil pan. The oil pan holds the engine oil, which lubricates the moving parts of the engine, reducing friction and preventing wear. How these components work together. Combustion process. When fuel is injected into the cylinder, it is compressed by the piston. A spark from the spark plug ignites the fuel-air mixture, causing combustion. The expanding gases push the piston downward, turning the crankshaft and generating power. Power transfer. The crankshaft's rotational motion is transferred to the transmission, which ultimately drives the wheels of the vehicle. Types of engine designs. Engine designs have a significant impact on vehicle performance, efficiency, and suitability for different applications. The most common engine designs are inline, V-type, and flat engines. Inline engines. Design. In an inline engine, all the cylinders are arranged in a straight line along the length of the engine. Common usage. Inline engines are commonly found in smaller vehicles, such as compact cars, sedans, and light trucks. Advantages. Compact design. Inline engines are easier and cheaper to manufacture. Smooth operation. These engines generally offer a smooth and reliable performance, especially in four-cylinder configurations. Example. The inline-4 engine is one of the most common engine configurations found in passenger vehicles. V-type engines. Design. In a V-type engine, the cylinders are arranged in two banks, forming a V shape. This configuration allows for a more compact engine design compared to inline engines. Common usage. V-type engines are used in larger vehicles, such as trucks, SUVs, and performance cars. Advantages. Powerful performance. V-type engines, such as V6 and V8 engines, provide higher power output, making them ideal for vehicles that require more horsepower and torque. Compactness. V-type engines are more compact than inline engines with the same number of cylinders, allowing for better weight distribution in vehicles. Example. The V8 engine is commonly used in trucks and high-performance sports cars. Flat engines. Design. In a flat engine, also called a boxer engine, the cylinders are arranged horizontally in two opposing banks, creating a flat design. This configuration provides a low center of gravity, enhancing vehicle stability. Common usage. Flat engines are often used in sports cars and performance vehicles. Advantages. Low center of gravity. The flat engine's design improves the handling and stability of the vehicle. Smooth operation. Flat engines are known for their smooth operation due to the opposing cylinders balancing each other out. Example. The Subaru Boxer engine and Porsche 911 use flat engines. Comparing engine designs. Here's a table comparing each engine design. I'll give you a few seconds to review the table. Conclusion and recap. In this lesson, we covered the essential components of an engine and how they work together to power a vehicle. We also explored different engine designs, including inline, V-type, and flat engines, and compared their advantages and applications. Understanding these engine fundamentals is key to your success on the ASE certification test and essential for anyone pursuing a career in automotive. Engine diagnosis. Course overview. Effective engine diagnosis is essential for identifying and resolving problems in vehicles, ensuring that they run smoothly and efficiently. This lesson will focus on common engine problems, their symptoms, and how to diagnose them using various diagnostic tools and equipment. By the end of this lesson, you will understand the typical engine issues encountered in the automotive field and how to approach diagnosing and resolving them. Common engine problems and symptoms. Engine diagnostics starts with recognizing the symptoms of common issues. These symptoms can often be observed during regular vehicle operation, but they can also be identified during routine maintenance or diagnostic procedures. Common engine problems and symptoms. Engine misfire. Symptoms are rough idling, hesitation, loss of power, and poor acceleration. Possible causes: faulty spark plugs, worn ignition coils, a clogged fuel injector, or a malfunctioning mass airflow sensor. Overheating engine. Symptoms are high temperature gauge readings, steam or coolant leaking from the engine, and a hot engine smell. Possible causes: low coolant levels, a broken thermostat, a malfunctioning water pump, or a damaged radiator. Poor fuel economy. Symptoms: the vehicle consumes more fuel than usual, requiring more frequent refueling. Possible causes: faulty oxygen sensors, clogged fuel injectors, incorrect tire pressure, or a malfunctioning engine control unit, ECU. Excessive smoke from exhaust. Symptoms: white, blue, or black smoke coming from the exhaust pipe. White smoke may indicate coolant leakage into the combustion chamber. Blue smoke often indicates oil burning due to worn valve seals or piston rings. Black smoke typically suggests an overly rich fuel mixture. Possible causes: leaking head gasket, worn piston rings, or a malfunctioning fuel system. Engine knock or pinging. Symptoms: a metallic knocking or pinging noise when accelerating or during heavy load. Possible causes: low-quality fuel, incorrect ignition timing, carbon buildup on the pistons, or worn spark plugs. Rough idling. Symptoms: the engine runs unevenly at idle, with vibrations or a fluctuating RPM gauge. Possible causes: faulty idle air control valve, dirty fuel injectors, or a vacuum leak in the intake system. Check engine light. Symptoms: the check engine light on the dashboard illuminates, indicating a potential issue. Possible causes: a range of issues, including malfunctioning sensors, misfiring, or emissions problems. Diagnostic approach. Start by gathering information about the symptoms from the vehicle owner or driver. Use a systematic approach to isolate the root cause of the issue, checking the most common causes first. Using diagnostic tools and equipment. Modern engines rely on complex systems that can be diagnosed with specialized tools. Using the correct diagnostic equipment is crucial for pinpointing engine issues and confirming suspicions about potential causes. Diagnostic tools. OBD2 scanner. Function. An OBD2 scanner is used to retrieve error codes from the vehicle's onboard computer. It helps identify issues with engine sensors, the ignition system, fuel system, and emissions control systems. How to use. Plug the OBD2 scanner into the vehicle's diagnostic port. This is usually located under the dashboard, and read the error codes. Common codes include P0300, which means misfire, and P0420, which means catalytic converter efficiency. Benefit: quick and effective way to identify malfunctioning systems and components. Compression tester. Function. A compression tester measures the compression levels of each cylinder in the engine. Low compression in one or more cylinders may indicate issues like worn piston rings, valve leaks, or a blown head gasket. How to use. Remove the spark plug from the cylinder, attach the compression tester, and crank the engine. Record the readings from each cylinder and compare them to the manufacturer's specifications. Benefit: helps identify internal engine problems related to compression. Vacuum gauge. Function. A vacuum gauge measures the vacuum pressure in the intake manifold, which is useful for diagnosing a variety of engine problems, including vacuum leaks, exhaust restrictions, and ignition timing issues. How to use. Attach the vacuum gauge to the intake manifold, start the engine, and observe the gauge readings. A steady, normal reading typically indicates a healthy engine. Benefit: provides insights into engine performance and helps identify problems like air intake leaks or clogged exhaust. Fuel pressure gauge. Function. This tool measures the pressure of fuel being delivered to the engine. Low fuel pressure can result in poor engine performance, rough idling, or misfires. How to use. Connect the fuel pressure gauge to the fuel rail or port, start the engine, and check the fuel pressure against manufacturer specifications. Benefit: allows you to assess fuel system performance and diagnose issues like a clogged fuel filter or failing fuel pump. Carbon monoxide meter. Function. A CO meter detects the levels of carbon monoxide in the exhaust, which can help identify issues with the combustion process, such as incomplete combustion or a malfunctioning catalytic converter. How to use. Attach the CO meter to the exhaust pipe, start the engine, and monitor the CO levels. Benefit: provides important diagnostic information regarding the engine's efficiency and emissions. Diagnostic flowchart for common issues. Step 1. Check for codes using an OBD2 scanner. Step 2. Conduct visual inspections for obvious issues. Step 3. Perform functional tests. Step 4. Review test results and compare them to manufacturer specifications. Step 5. Identify and repair the faulty components. Conclusion and recap. In this lesson, we explored the basics of engine diagnosis, including common engine problems and their symptoms. We also discuss the diagnostic tools and equipment used to identify and resolve engine issues. By using the right tools and following a systematic approach, you can accurately diagnose engine problems and perform effective repairs. Engine maintenance. Engine maintenance is a critical aspect of keeping vehicles running efficiently and reliably. Proper maintenance tasks, such as oil changes and cooling system checks, help prevent engine wear and extend the life of the vehicle. This lesson will guide you through essential engine maintenance tasks, including engine oil and filter changes, and cooling system checks and repairs. By mastering these fundamental skills, you will be well prepared for the ASE certification test and equipped to maintain and service engines in the real world. Engine oil and filter change. An engine oil and filter change is one of the most common and important maintenance tasks in any vehicle. This procedure helps to keep the engine lubricated, reducing friction and wear, and ensures that contaminants are removed from the engine. Why is engine oil important? Lubrication. Oil helps to lubricate the moving parts of the engine, preventing friction and wear. Cleaning. Oil helps to clean the engine by carrying away dirt, debris, and contaminants. Cooling. Oil also helps to dissipate heat from the engine, keeping temperatures within safe operating limits. Sealing. Oil helps seal the gaps between engine parts, such as the piston rings, improving compression and performance. Steps for performing an oil and filter change. Step 1. Prepare the vehicle. Ensure the vehicle is on a level surface and the engine is off. Raise the vehicle if needed using a jack and secure it with jack stands. Tip: make sure the engine is slightly warm, not hot, to help drain the oil more effectively. Step 2. Drain the old oil. Place an oil drain pan under the oil drain plug. Using the correct wrench, loosen the oil drain plug and allow the oil to fully drain into the pan. Tip: allow sufficient time for all the oil to drain to avoid mixing old oil with fresh oil. Step 3. Remove and replace the oil filter. Use an oil filter wrench to remove the old filter. Be sure to have a rag or towel ready to catch any residual oil. Before installing the new filter, lightly lubricate the rubber gasket on the new filter with some fresh oil. This ensures a proper seal. Screw the new filter in place, tightening it according to the manufacturer's specifications. Step 4. Replace the drain plug. Once all the oil has drained, replace the drain plug and tighten it with a wrench. Be careful not to over-tighten, as this can damage the threads. Step 5. Add new oil. Use the manufacturer's recommended oil type and quantity. Remove the oil filler cap and pour in the new oil, checking the oil level with a dipstick. Tip: add the recommended amount of oil, then check the level and top off as necessary. Step 6. Check for leaks. Start the engine and let it run for a few minutes. Check for any oil leaks around the drain plug and oil filter. Tip: ensure the oil pressure light goes off and the oil level is correct. Step 7. Dispose of the old oil and filter. Take the used oil and filter to a local recycling center. Never dispose of engine oil in the trash or down a drain. Here are common mistakes to avoid: using the wrong type or amount of oil, overfilling the oil, forgetting to lubricate the oil filter gasket, neglecting to dispose of old oil properly. Cooling system checks and repairs. The cooling system plays a vital role in maintaining the engine's temperature by dissipating excess heat. If the cooling system malfunctions, it can lead to overheating, engine damage, or even complete engine failure. Regular checks and maintenance are essential for preventing such issues. Cooling system components. Radiator. The radiator cools the engine coolant by allowing air to pass through it. The coolant absorbs heat from the engine and releases it through the radiator. Water pump. The water pump circulates coolant through the engine, ensuring it stays at the proper temperature. Thermostat. The thermostat regulates the temperature of the coolant, opening and closing to maintain the engine at an optimal operating temperature. Radiator hoses. These hoses carry coolant between the radiator, engine, and thermostat. Coolant/antifreeze. The coolant absorbs heat and helps prevent the engine from freezing in cold temperatures. Steps for performing cooling system checks and repairs. Check coolant levels. Before checking the coolant level, ensure the engine is cool. Locate the radiator reservoir and check the coolant level. If it's low, top it off with the appropriate type of coolant. Tip: always use the manufacturer's recommended coolant to avoid damage to the cooling system. Inspect radiator and hoses. Inspect the radiator for any visible damage, leaks, or blockages. Check the radiator fins to ensure they are not clogged with debris. Inspect all coolant hoses for cracks, bulges, or leaks. If any hoses appear damaged, they should be replaced immediately. Tip: check the hoses when the engine is cold to avoid burns from hot coolant. Check the water pump. Inspect the water pump for any signs of leakage around the pump shaft or housing. A leaking water pump should be replaced. Listen for unusual noises while the engine is running, as a failing water pump may produce a whining or grinding noise. Tip: if the water pump is leaking, it may require a full replacement as it cannot be repaired. Test the thermostat. The thermostat controls the engine temperature by regulating the coolant flow. A malfunctioning thermostat may cause the engine to overheat or run too cold. To test the thermostat, remove it from the engine and place it in hot water. It should open at the manufacturer's specified temperature. Tip: if the thermostat is not functioning correctly, replace it. Flush the radiator. Over time, the cooling system can accumulate rust, scale, and other debris that can clog the radiator and affect performance. A radiator flush can help remove these contaminants. To flush the system, drain the coolant and run water through the radiator until it runs clear. Tip: after flushing, replace the coolant with the recommended mixture of coolant and water. Check for leaks. Inspect all connections, hoses, and components for coolant leaks. If any leaks are found, replace the faulty parts. Tip: a pressure test can be used to identify hidden leaks in the cooling system. Here are the common cooling system issues. Overheating, caused by low coolant levels, a faulty thermostat, or a failing water pump. Leaking coolant, often caused by cracked hoses, a broken radiator, or a failing water pump. And poor heater performance, can be due to a low coolant level or a clogged heater core. Conclusion and recap. In this lesson, we've covered essential engine maintenance tasks, including how to perform an oil change and inspect and maintain the cooling system. These maintenance procedures are vital to keeping the engine running efficiently and preventing costly repairs. By mastering these skills, you'll be well prepared for the ASE certification test and gain valuable hands-on experience for the automotive service industry. Engine repair. Engine repair is an essential skill for any automotive technician. The ability to disassemble, repair, and reassemble engines is critical for diagnosing and addressing issues in various engine components. This lesson will focus on the key aspects of engine repair, including the procedures for removing, disassembling, and reassembling engines, as well as repairing common internal engine components, such as pistons, valves, and crankshafts. By the end of this lesson, you will have the foundational knowledge and skills needed to perform successful engine repairs, an essential aspect of the ASE certification test. Removing, disassembling, and reassembling engines. Engine removal and disassembly require careful planning and attention to detail to avoid damaging components. Reassembling the engine correctly ensures that it will run smoothly and efficiently once it is back in the vehicle. Step 1. Removing the engine from the vehicle. Removing an engine from a vehicle is often the first step in performing repairs. This can be a complex process depending on the vehicle, but the general steps are as follows. Prepare the vehicle. Raise the vehicle using a lift or jack stands, and ensure it is stable and secure. Disconnect the battery to prevent any electrical issues during the removal process. Drain all fluids, including coolant, oil, and fuel, to avoid spills during removal. Disconnect components. Remove any external components that may obstruct the engine's removal, such as the air intake, exhaust manifold, fuel lines, and hoses. Detach the engine from the transmission by removing bolts that connect the engine to the gearbox. Ensure the vehicle is in neutral or park before attempting this step. Support the engine. Use an engine hoist or crane to support the engine before removing the mounting bolts. Carefully lift the engine from its mount and remove any remaining bolts securing it to the vehicle. Engine removal. Once all connections have been removed and the engine is properly supported, carefully lift the engine out of the vehicle. Be mindful of surrounding components to avoid damage. Step 2. Disassembling the engine. Once the engine is removed from the vehicle, it is time to disassemble it for inspection and repair. Place the engine on a secure workbench. Ensure the engine is placed securely on an engine stand or workbench to avoid injury or damage. Keep the work area clean and organized to avoid losing small parts during the disassembly. Remove external components. Begin by removing external parts like the intake manifold, exhaust manifolds, cylinder heads, and timing belt or chain. Use a torque wrench and follow manufacturer guidelines to avoid over-tightening bolts. Inspect for wear and damage. As you disassemble each part, carefully inspect it for signs of wear, cracking, or damage. Common issues include worn piston rings, damaged valves, or cracked cylinder heads. Document the process. Document the disassembly process, taking notes or photos of the position and condition of each component. This will help during reassembly. Step 3. Reassembling the engine. Reassembling the engine correctly is just as important as disassembling it. Follow these steps. Clean all components. Clean all parts thoroughly before reassembling, especially the cylinder head and pistons. Use solvent or engine cleaner to remove any carbon buildup or debris. Replace worn or damaged parts. Replace any worn-out components, such as gaskets, seals, or piston rings. Ensure that all replacement parts meet the manufacturer's specifications. Reassemble in reverse order. Begin reassembling the engine by following the reverse order of disassembly. Attach the cylinder heads, intake manifold, exhaust manifolds, and other components as needed. Tip: tighten all bolts to the correct torque specifications to avoid damaging the engine. Check for proper clearances and timing. Ensure that all components are installed correctly and that clearances are within the manufacturer's specifications. Double-check the timing of the camshaft, crankshaft, and valves. Final inspection. After reassembling the engine, inspect all connections and ensure that no parts are left loose. Verify that all fluids are replaced and the engine is properly lubricated. Repairing internal engine components. Internal engine components are critical to engine function, and repairing or replacing them when they become damaged is essential for maintaining engine performance. Common internal engine components and repair methods: pistons and piston rings. Symptoms of damage: worn piston rings, poor compression, or excessive oil consumption. Repair process: piston rings may need to be replaced if they are worn or damaged. Replacing pistons requires removing the cylinder head and carefully disassembling the engine. Valves: symptoms of damage: low compression, poor fuel economy, or misfires. Repair process: damaged valves may require reconditioning or replacement. Valve seats should be inspected and reground to ensure a proper seal. Camshaft and timing components. Symptoms of damage: poor engine performance, timing issues, or noisy engine operation. Repair process: the camshaft may need to be replaced if it is worn. The timing chain or belt should also be checked for wear and replaced if necessary. Crankshaft: symptoms of damage: vibration, knocking, or engine oil contamination. Repair process: if the crankshaft is worn or damaged, it may need to be reground or replaced. Crankshaft bearings should be inspected and replaced if needed. Cylinder head: symptoms of damage: overheating, coolant leaks, or loss of compression. Repair process: the cylinder head may need to be resurfaced or replaced if cracked. Valve seals and gaskets should also be checked and replaced if damaged. Conclusion and recap. In this lesson, we've covered essential engine repair techniques, including the correct procedures for removing, disassembling, and reassembling engines, as well as repairing internal engine components such as pistons, valves, and camshafts. These repair skills are crucial for anyone preparing for the ASE certification test and are fundamental to the daily work of automotive technicians. Automatic transmissions and transaxles. The ASE Certification Test A2, Automatic Transmissions and Transaxles, evaluates your knowledge of the complex systems that allow a vehicle to shift gears automatically. This lesson focuses on the core components of automatic transmissions and how they operate. Understanding the fundamental parts of an automatic transmission, such as the torque converter, clutch pack, and planetary gears, is critical for passing the ASE A2 test and performing maintenance and repairs on these systems in real-world applications. Basic operation of automatic transmissions. Automatic transmissions are designed to automatically change the gear ratio as the vehicle moves, freeing the driver from needing to manually shift gears. The operation of an automatic transmission involves several key components working together to select the appropriate gear based on the vehicle's speed and engine load. Key functions of automatic transmissions. Shifting gears. Automatic transmissions use a combination of hydraulic pressure, mechanical components, and electronic controls to change gears. These shifts are based on factors like vehicle speed and throttle position. Torque conversion. Unlike manual transmissions, which use a clutch to engage and disengage gears, automatic transmissions use a torque converter to transfer power from the engine to the transmission. Smooth power transfer. The transmission ensures smooth shifting and power transfer, allowing the vehicle to accelerate and decelerate smoothly without the need for driver intervention. The role of the transmission fluid. Transmission fluid serves several important functions in an automatic transmission. Lubrication. It lubricates the moving parts within the transmission to reduce friction and wear. Hydraulic fluid. It provides the hydraulic pressure needed to operate components like the torque converter and clutch packs. Cooling. It helps dissipate heat generated by the transmission during operation. Key components of automatic transmissions. Several essential components work together to allow the automatic transmission to function smoothly. Let's break down the role and function of the torque converter, clutch pack, and planetary gears. Torque converter. Function. The torque converter is a fluid coupling that connects the engine to the transmission, allowing power to be transferred smoothly from the engine to the drivetrain. Components of the torque converter. Stator. The stator redirects fluid flow from the turbine to the pump, multiplying torque at low speeds. Pump. The pump creates the hydraulic pressure that controls the transmission's shifting. Turbine. The turbine is connected to the input shaft of the transmission and receives power from the pump. It rotates when fluid is sent from the pump, transferring energy to the transmission. Operation. The torque converter allows the engine to keep running when the vehicle is stationary. It ensures the smooth transfer of power when the vehicle starts moving and helps manage the engine's power as the car accelerates or decelerates. Lockup torque converter. Modern transmissions may feature a lockup torque converter, which locks the converter when the vehicle reaches cruising speed. This improves fuel efficiency by eliminating slippage between the pump and turbine. Clutch pack. Function. A clutch pack is a series of friction discs and steel plates that engage and disengage gears in the transmission. The clutch pack works with hydraulic pressure to shift the transmission between gears. Components. Friction discs. These discs are coated with a material that provides the friction needed to transmit power from one part of the transmission to another. Steel plates. These plates help provide structural support for the clutch pack and facilitate smooth gear engagement. Hydraulic pressure. Hydraulic fluid is used to press the clutch pack components together, causing the transmission to engage or disengage a specific gear. Operation. When the vehicle is accelerating, the clutch pack applies pressure to specific gears to engage them. This pressure allows the vehicle to smoothly change gears without the need for driver intervention. In a multi-speed transmission, multiple clutch packs are used to engage the various gear ratios. Planetary gear set. Function. The planetary gear set is the core component of most automatic transmissions. It allows the transmission to shift between multiple gears with a single set of components. Components. Sun gear, the central gear that drives the planetary gears. Planet gears, gears that rotate around the sun gear. They are the driving force behind shifting and provide different gear ratios. Ring gear, the outer gear that surrounds the planet gears. The ring gear helps determine the output speed and torque. Carrier, the housing that holds the planet gears in place and allows them to rotate around the sun gear. Operation. The planetary gear set allows for multiple gear ratios using a single set of gears. By engaging different combinations of the sun, planet, and ring gears, the transmission can produce various gear ratios for different driving conditions. The transmission's electronic control unit, ECU, and hydraulic pressure control, which gears in the planetary gear set, are engaged during operation. Summary of automatic transmission operation. To summarize the operation of an automatic transmission, the torque converter transfers engine power to the transmission using hydraulic fluid. The clutch packs engage or disengage the gears, allowing the transmission to shift between different gear ratios. The planetary gear set controls the various gear ratios, helping the vehicle operate at different speeds with optimal engine efficiency. Together, these components ensure that the vehicle shifts smoothly without the need for the driver to manually change gears. Conclusion and recap. In this lesson, we covered the basic operation of automatic transmissions and focused on key components such as the torque converter, clutch packs, and planetary gear sets. These components work together to ensure the smooth operation of the vehicle, shifting gears automatically based on driving conditions. Understanding these components is essential for anyone preparing for the ASE Certification Test A2 and for diagnosing and repairing automatic transmissions. Transmission diagnostics. The ability to diagnose transmission problems accurately is a critical skill for automotive technicians. This lesson will focus on how to identify common transmission issues, perform diagnostic tests, and apply troubleshooting techniques to resolve those issues. By the end of this lesson, learners will be equipped with the knowledge and skills needed to identify and address common transmission failures and perform effective diagnostics. Diagnosing transmission problems. Diagnosing transmission issues requires careful observation of symptoms and a methodical approach to testing. The key to successful diagnosis is gathering all relevant data, understanding the symptoms, and isolating the source of the problem. Common symptoms of transmission problems: slipping gears. Symptoms: the transmission unexpectedly shifts gears, often resulting in a loss of power or sudden acceleration. In some cases, the transmission may seem to slip out of gear. Possible causes: low transmission fluid, a malfunctioning torque converter, or worn-out clutch packs or bands. Harsh or delayed shifting. Symptoms: when shifting gears, the transmission shifts roughly or with noticeable delays. Possible causes: low fluid levels, dirty fluid, or a problem with the valve body or solenoids. Overheating. Symptoms: the engine temperature rises above normal, and you may notice a burning smell or a slipping transmission. Possible causes: low fluid levels, fluid contamination, or a clogged transmission cooler. Noisy operation. Symptoms: grinding or whining noises while the vehicle is in gear. Possible causes: worn gears, a malfunctioning torque converter, or damaged bearings. Check engine light. Symptoms: the transmission-related check engine light illuminates on the dashboard. Possible causes: issues detected by the vehicle's onboard diagnostic system, such as faulty sensors, solenoids, or wiring. Fluid leaks. Symptoms: transmission fluid pooling under the vehicle when parked. Possible causes: damaged seals, gaskets, or pan bolts. Conducting a visual inspection. Fluid condition. Inspect the transmission fluid for color and consistency. Healthy fluid should be a clear red or pink color. Dark, brown, or burnt fluid can indicate overheating or contamination. Fluid level. Check the fluid level according to the manufacturer's specifications. Low fluid levels may be a sign of a leak or inadequate fluid circulation. External leaks. Look for signs of transmission fluid leaks around the seals, gaskets, and cooler lines. Using diagnostic tools, OBD2 scanner. An OBD2 scanner is essential for retrieving diagnostic trouble codes that point to transmission issues. The scanner can indicate problems like a faulty solenoid, torque converter, or sensor. Pressure testing. Use a pressure gauge to check the hydraulic pressure in the transmission. Low pressure may indicate a problem with the pump, solenoids, or valve body. Transmission fluid temperature sensor. Overheating is a common transmission problem. Use the temperature sensor to monitor fluid temperature during operation to ensure it stays within the optimal range. Common failure modes and troubleshooting techniques. Once you've identified the symptoms of a transmission problem, the next step is determining the cause and applying appropriate troubleshooting techniques. Below are some common failure modes and solutions. Slipping gears. Problem: transmission slips in and out of gears or won't stay in gear. Possible causes: low fluid levels or dirty fluid, worn out clutch packs, friction plates, or valve body components. Troubleshooting: check fluid level, add or replace transmission fluid as needed. Inspect the clutch packs. Look for signs of wear or overheating. If the clutch packs are worn, replacement may be necessary. Check the valve body. Ensure the valve body is operating correctly and not causing erratic shifting. Harsh or delayed shifting. Problem: the vehicle shifts with a jolt or delay between gears. Possible causes: dirty or contaminated transmission fluid, a malfunctioning valve body or shift solenoids, worn or broken shift bands. Troubleshooting: replace the fluid. If the fluid is dirty or contaminated, perform a transmission flush and replace it with fresh fluid. Inspect solenoids. Use an OBD2 scanner to check for solenoid-related codes. Test or replace malfunctioning solenoids. Check the valve body. Inspect the valve body for clogs, wear, or damage. Clean or replace as needed. Overheating. Problem: the transmission overheats, often resulting in slipping or burning smells. Possible causes: low fluid levels or degraded fluid, a clogged transmission cooler or radiator, excessive towing or heavy driving conditions. Troubleshooting: check the fluid. Ensure the fluid is clean and at the correct level. Replace fluid if it's overheated or contaminated. Inspect the transmission cooler. Ensure the cooler and radiator are not clogged or damaged, which can cause poor heat dissipation. Monitor driving conditions. Avoid towing or driving in heavy conditions until the issue is resolved. Fluid leaks. Problem: transmission fluid leaks from the vehicle. Possible causes: worn seals or gaskets, loose pan bolts, cracked transmission housing. Troubleshooting: inspect seals and gaskets. Check around the pan, tail shaft, and cooler lines for leaks. Replace any worn or damaged seals. Tighten pan bolts. Loose bolts can cause fluid to leak from the pan. Check transmission housing. Inspect the transmission case for cracks. If cracks are found, the transmission may need to be replaced. Noise from the transmission. Problem: grinding, whining, or rattling noises from the transmission. Possible causes: worn bearings, gears, or torque converter. Lack of lubrication due to low fluid. Troubleshooting: check fluid levels. Ensure the transmission is filled with the correct fluid and at the correct level. Inspect bearings and gears. Look for signs of wear or damage. Replace worn bearings or gears as necessary. Check the torque converter. If the noise is related to the torque converter, inspect or replace it. Conclusion and recap. In this lesson, we covered the diagnosis of common transmission problems, including symptoms, causes, and troubleshooting techniques. By understanding these diagnostic processes and using the right tools, you will be well equipped to handle transmission-related issues in both the ASE certification test and real-world repair situations. Transmission repair and maintenance. Transmission repair and maintenance are crucial for ensuring that vehicles operate smoothly and reliably. Proper fluid checks, changes, and the ability to rebuild or replace internal transmission components are essential skills for anyone in the automotive repair industry. This lesson will provide you with the knowledge and skills needed to perform fluid checks and changes, and rebuild or replace internal transmission components. Mastering these skills will prepare you for both the ASE certification test and real-world transmission repair tasks. Performing fluid checks and changes. Transmission fluid is essential for the operation of the transmission system, providing both lubrication and hydraulic pressure. Regular fluid checks and changes help prevent transmission failure and ensure smooth operation. Importance of transmission fluid. Lubrication reduces friction between moving components such as gears, bearings, and the torque converter, preventing wear and damage. Hydraulic pressure. Transmission fluid provides the hydraulic pressure necessary to operate the clutch packs, solenoids, and other components within the transmission. Cooling helps dissipate the heat generated by the transmission during operation. Checking transmission fluid levels. Warm the vehicle. Start the vehicle and allow it to reach operating temperature. This ensures that the fluid is at the correct level and temperature. Locate the dipstick. Most automatic transmissions have a dipstick for checking the fluid level. It is typically located near the engine or under the vehicle. Check fluid level. Remove the dipstick, wipe it clean, and reinsert it fully. Remove it again to check the fluid level. The fluid level should be within the full range marked on the dipstick. Tip: if the level is low, add the manufacturer recommended fluid to the correct level. Inspecting transmission fluid condition. Color. Healthy transmission fluid is typically red or pink. If the fluid is dark brown or black, it may be burnt, which could indicate overheating or contamination. Smell. Burnt fluid has a distinct burnt smell. If the fluid smells burnt, it may indicate problems with the transmission. Texture. Check for any particles or debris in the fluid. If the fluid feels gritty, it could be a sign of internal wear in the transmission. Changing transmission fluid. Changing the transmission fluid involves draining the old fluid, replacing the filter, and refilling with fresh fluid. Prepare the vehicle. Raise the vehicle using a lift or jack stands to access the transmission pan. Place a catch pan under the transmission pan to collect the old fluid. Drain the old fluid. Loosen the bolts on the transmission pan and carefully remove it. Let the fluid drain completely into the pan. Tip: some vehicles may have a drain plug on the transmission pan for easier fluid removal. Replace the filter. Most transmissions have a filter that helps catch contaminants. Remove and replace the filter according to the manufacturer's instructions. Install the pan and add new fluid. Replace the pan with a new gasket, ensuring that it's properly secured. Refill the transmission with the recommended fluid type and quantity, checking the level using the dipstick. Rebuilding and replacing internal transmission components. Over time, internal transmission components can wear out, leading to poor performance or complete failure. Rebuilding or replacing these components is a more advanced maintenance procedure that requires careful attention to detail. Common internal transmission components. Valve body. The valve body regulates the flow of transmission fluid to different components, such as the clutch packs. It acts as the brain of the transmission, controlling fluid direction and pressure. Clutch packs. These are made up of multiple friction discs and steel plates that engage or disengage gears as needed. Planetary gear set. The planetary gear set provides different gear ratios and is the core component of the transmission's gear shifting ability. Torque converter. The torque converter transfers power from the engine to the transmission using fluid. It is a critical component for automatic transmission operation. Removing the transmission. Before repairing internal transmission components, the transmission must be removed from the vehicle. This requires the following steps. Prepare the vehicle. Raise the vehicle using a lift or jack stands and secure it safely. Disconnect the battery and drain all fluids to avoid spills. Disconnect the transmission. Remove the drive shaft, exhaust components, and any electrical connections attached to the transmission. Disconnect the transmission from the engine by removing the bolts that connect the transmission bell housing to the engine block. Support the transmission. Use a transmission jack or hoist to support the weight of the transmission while you remove it from the vehicle. Remove the transmission. Carefully lift the transmission from the vehicle, ensuring that it is balanced and secure during the process. Disassembling the transmission. Once the transmission is removed, it's time to disassemble it for inspection and repair. Remove the transmission pan. Drain any remaining fluid and remove the transmission pan to access the internal components. Inspect the valve body. The valve body contains several passages and solenoids. Check for clogs, wear, or damage. If the valve body is faulty, it may need to be replaced or cleaned. Inspect the clutch packs. Remove the clutch packs and inspect the friction discs and steel plates for wear or damage. Replace any worn parts. Examine the planetary gear set. Check the planetary gears for excessive wear or damage. If any gears are worn or chipped, they must be replaced. Rebuilding the transmission. Rebuilding involves replacing worn components and reassembling the transmission to restore its functionality. Clean all components. Thoroughly clean all components, including the valve body, planetary gear set, and clutch packs, using appropriate cleaning solutions and brushes. Replace worn parts. Replace any worn or damaged parts, including seals, gaskets, clutch discs, and bearings. Ensure that all parts meet the manufacturer's specifications. Reassemble the transmission. Begin reassembling the transmission in the reverse order of disassembly. Be sure to follow manufacturer guidelines for torque specifications and part placement. Test the rebuilt transmission. Once the transmission is reassembled, test it before reinstalling it in the vehicle. Check for proper fluid flow, gear engagement, and smooth shifting. Conclusion and recap. In this lesson, we covered the essential aspects of transmission repair and maintenance, including performing fluid checks and changes, and the process of rebuilding and replacing internal transmission components. Mastery of these tasks is vital for anyone preparing for the ASE certification test and is essential for successful transmission repair in real-world applications. Manual drivetrains and axles A3. Manual transmissions are one of the most essential components in vehicles that provide a manual driving experience. They rely on a combination of mechanical and hydraulic systems to engage gears and transfer power from the engine to the wheels. In this lesson, we will dive deep into the fundamentals of manual transmissions, covering how they work, the role of the clutch, the shifting mechanisms, and the gearbox. Mastery of these concepts is critical for the ASE Certification Test A3 and for understanding how manual drivetrains and axles function in vehicles. Understanding how manual transmissions work. A manual transmission, also known as a standard transmission, allows the driver to control the vehicle's speed and torque by manually selecting different gears. It uses a combination of mechanical components, including the clutch, gear lever, and gearbox, to connect the engine to the drivetrain. Key functions of a manual transmission. Power transmission. The manual transmission is responsible for transmitting power from the engine to the wheels while allowing the driver to control vehicle speed by selecting the appropriate gear. Torque adjustment. By changing gears, the transmission adjusts the torque output to match the driving conditions, such as accelerating, cruising, or slowing down. Components of a manual transmission system. Engine, the power source for the manual transmission. Clutch, disconnects the engine from the transmission to allow smooth shifting between gears. Gear lever, used by the driver to manually select the appropriate gear. Gearbox, the core of the transmission system, containing the gears that provide different torque ratios. Drive shaft, transfers power from the gearbox to the wheels. Clutch operation, shifting mechanisms, and gearboxes. The clutch. The clutch is a vital component that engages and disengages the engine from the transmission, allowing the driver to change gears smoothly without stalling the engine. Function of the clutch. The clutch's primary function is to disconnect the engine from the transmission temporarily, allowing the driver to shift gears without the engine's power being transmitted to the wheels. Clutch components. Clutch pedal. The driver operates the clutch by pressing the pedal to disengage the engine from the transmission. Clutch disc, the friction surface that engages with the flywheel to transmit power. Flywheel, the large disc attached to the engine that the clutch disc presses against. Pressure plate, a spring-loaded device that presses the clutch disc against the flywheel. Release bearing, a bearing that engages and disengages the clutch disc from the flywheel. How the clutch works. Pressing the pedal. When the driver presses the clutch pedal, the release bearing pushes against the pressure plate, causing the clutch disc to disengage from the flywheel. This disconnects the engine from the transmission, allowing the driver to shift gears. Releasing the pedal. Once the driver selects the desired gear, releasing the pedal gradually engages the clutch disc with the flywheel, transferring engine power to the transmission. Shifting mechanisms. Shifting gears in a manual transmission involves using a gear lever or shifter to select different gears. Each gear provides a specific ratio of power and speed. Gear lever. The driver uses the gear lever to select the desired gear. This lever is connected to a shift fork and shift rods inside the transmission. Shift fork and rods. The shift fork moves the shift rods inside the transmission, which then move the gear synchronizers into position to engage the selected gear. Synchronizers. Synchronizers are components that match the speed of the gear and shaft, allowing for smooth engagement without grinding. They are crucial for preventing damage to gears and for ensuring smooth shifts. Gearbox. The gearbox houses all the gears and the associated components that allow the manual transmission to function. It is responsible for adjusting the torque and speed sent to the drive shaft and ultimately to the wheels. Basic gearbox design. The gearbox consists of several gears of different sizes that mesh with one another. In constant mesh gearboxes, all gears are constantly engaged, but only one gear is connected to the output shaft at a time, depending on the selected gear. In sequential gearboxes, the gears engage in a specific sequence, commonly used in racing applications. Types of gearbox configurations. H-pattern gearbox. Commonly found in passenger vehicles, where the gear lever follows an H pattern for gear selection. Dogbox gearbox. A type of gearbox where the gears engage through dog teeth, commonly used in racing applications for quicker gear shifts. Synchro mesh gearbox. A gearbox that uses synchronizers to help match the speed of gears during shifting, ensuring smooth transitions. The gear ratios. Each gear in the transmission provides a specific ratio of input to output. Lower gears provide more torque and are used for acceleration, while higher gears provide higher speeds and are used for cruising. Low gears provide high torque and are used for starting the vehicle or driving at low speeds. High gears provide lower torque but higher speed, used for highway cruising. Summary of manual transmission operation. To summarize how the manual transmission works, the engine's power is transferred to the transmission via the clutch. The gear lever is used to select the appropriate gear, controlling the amount of torque and speed sent to the wheels. The gearbox consists of gears that adjust the power from the engine and allow the vehicle to operate efficiently at different speeds. Conclusion and recap. In this lesson, we covered the fundamentals of manual transmissions, including how the clutch operates, the shifting mechanisms, and the gearbox. Understanding these components and how they work together is critical for diagnosing, maintaining, and repairing manual transmission systems. This knowledge is essential for anyone preparing for the ASE Certification Test, A3, and for anyone working in automotive repair. Drivetrain diagnosis. Diagnosing issues within the drivetrain system is an essential skill for automotive technicians. This lesson will focus on how to diagnose common drivetrain problems, such as noise and vibration, and provide guidance on troubleshooting differential issues. Mastery of these diagnostic skills is critical for the ASE certification test and for effectively addressing drivetrain problems in the field. Diagnosing drivetrain noise and vibration. Noise and vibration in the drivetrain can indicate a variety of issues, from worn bearings to misaligned drive shafts. The key to diagnosing these issues is identifying the source of the noise or vibration and understanding the possible causes. Common drivetrain noises and their causes. Grinding or whining noise. Symptoms. A grinding or whining noise when accelerating or decelerating. Possible causes. Worn bearings. If the bearing in the transmission, differential, or wheel hub is worn, It can cause a grinding or whining noise. Faulty gears. A whining noise can also indicate worn or damaged gears in the differential or transmission. Transmission fluid issues. Low or contaminated fluid in the transmission can cause the gears to make noise. Clunking or banging noise. Symptoms: a loud clunking sound when shifting or during acceleration. Possible causes: loose or worn universal joints. U-joints allow for the rotation of the driveshaft and can cause a clunking noise if they are damaged or excessively worn. Worn differential gears. A worn differential or axle gears can also create a clunking noise when power is applied or released. Squealing or chirping noise. Symptoms: a high-pitched squealing or chirping noise while driving. Possible causes: worn serpentine belt. The serpentine belt that powers the alternator, power steering, and other accessories can cause a squeal when it becomes worn. Misaligned or dry pulleys. Pulley misalignment or dry pulleys can lead to chirping or squealing noises. Humming or rubbing noise. Symptoms: a consistent humming or rubbing noise, often related to the wheel or axle area. Possible causes: worn wheel bearings. A humming noise, especially when turning, may indicate a worn wheel bearing. Brake issues. Rubbing noises may be caused by brake pads rubbing against the rotor, indicating misalignment or worn components. Diagnosing drivetrain vibrations. Steering wheel vibration. Symptoms: vibration felt in the steering wheel while driving at certain speeds. Possible causes: imbalanced tires or wheels. An imbalance in the tires or wheels can cause vibration, particularly at higher speeds. Worn steering components. Worn steering rack or tie rods can also lead to vibration in the steering wheel. Body or seat vibration. Symptoms: vibration felt in the vehicle's body or seat while driving. Possible causes: out-of-balance driveshaft. An unbalanced driveshaft can cause vibration, especially at higher speeds. Worn universal joints. Worn U-joints can create vibration in the drivetrain, particularly when accelerating or decelerating. Vibration when turning. Symptoms: vibration felt when turning the vehicle, particularly at low speeds. Possible causes: faulty CV joints. Constant velocity joints that connect the driveshaft to the wheel hubs can wear out and cause vibration when turning. Differential issues. Problems with the differential, such as worn gears or bearing. Differential diagnosis and troubleshooting. The differential is responsible for allowing the wheels to rotate at different speeds, especially when turning. Diagnosing and troubleshooting issues with the differential is crucial to ensuring smooth operation. Common differential problems. Whining or howling noise. Symptoms: a continuous whining or howling noise, often worsening when accelerating. Possible causes: worn differential gears. Gear wear or improper gear alignment can create a whining noise, particularly when under load. Low or contaminated differential fluid. Low or dirty fluid in the differential can cause the gears to become noisy. Grinding or clunking noise. Symptoms: a grinding or clunking noise during acceleration or deceleration. Possible causes: worn differential bearings. Worn bearings in the differential can lead to a grinding noise. Broken or damaged gears. If the gears in the differential are chipped or broken, they can cause a clunking noise. Leaking fluid. Symptoms: fluid leaking from the differential, often leading to low fluid levels. Possible causes: worn seals or gaskets. Differential seals and gaskets can wear out over time, causing fluid leaks. Damaged differential housing. Cracks or damage to the differential housing can also lead to fluid leaks. Diagnosing differential issues. Fluid level and condition. Check fluid level. Ensure the differential fluid is at the correct level. If it's low, add the appropriate fluid. Check fluid condition. The fluid should be clean and free of debris. If the fluid appears dark, gritty, or smells burnt, It may need to be replaced. Noise diagnosis. Identify the noise source. Listen carefully to the noise and determine if it's coming from the front, rear, or side of the vehicle. This can help pinpoint which differential is causing the issue. Test under load. Drive the vehicle under load, e.g. during acceleration, to see if the noise worsens or changes. Inspect gears and bearings. Check for wear. Inspect the gears, bearings, and seals for visible damage or wear. Worn components should be replaced. Check gear alignment. Ensure the gears are properly aligned and there is no excessive backlash between the gears. Conclusion and recap. In this lesson, we covered how to diagnose drivetrain noise and vibration and provided a detailed guide to differential diagnosis and troubleshooting. Understanding these common issues and having the diagnostic tools to identify and resolve them is essential for any automotive technician, especially when preparing for the ASE certification test. Axles and bearings. Axles and bearings are critical components of a vehicle's drivetrain system. They help transfer power from the engine to the wheels while ensuring smooth rotation and stability. Diagnosing and repairing axle shaft and bearing problems, as well as removing and replacing axle assemblies, are essential skills for an automotive technician. This lesson will provide a detailed understanding of how to identify, repair, and replace axle and bearing components. By mastering these skills, you will be well prepared for the ASE certification test and equipped to handle these repairs in a real-world environment. Diagnosing and repairing axle shaft and bearing problems. Axles and bearings play a vital role in a vehicle's performance, and diagnosing issues with them requires a thorough understanding of their functions and common problems. Common axle shaft problems. Axle shaft noise. Symptoms: a whining, grinding, or clunking noise that increases with speed and turns. Possible causes: worn axle shaft bearings. Bearings that support the axle shaft can wear out over time, leading to noise and vibration. Damaged axle shaft. A bent or damaged axle shaft can cause excessive vibration and noise during driving. Axle shaft vibration. Symptoms: vibration that occurs during acceleration or deceleration, felt in the steering wheel or the seat. Possible causes: out-of-balance axle shaft. Axles that are not properly balanced can cause vibrations at certain speeds. Worn universal joints, U-joints. U-joints that connect the axle shafts to the drive shaft can wear out, leading to vibration. Axle shaft leaks. Symptoms: fluid leaking from the axle assembly, often seen around the axle seal. Possible causes: worn or damaged axle seals. Seals that keep fluid inside the differential or axle housing can wear out, leading to leaks. Cracked axle housing. A crack in the axle housing can lead to fluid leakage. Common bearing problems. Noise from wheel bearings. Symptoms: a growling, humming, or whirring noise that increases with speed and may change when turning. Possible causes: worn wheel bearings. Bearings that support the wheel hub can wear out, leading to noise and eventual failure. Contaminated bearing. Dirt or water ingress can damage the bearings and lead to premature wear. Wheel bearing vibration. Symptoms: vibration in the steering wheel or body of the vehicle, especially when turning. Possible causes: worn or damaged bearings. Bearings that support the wheel hub can cause vibration if they are damaged or worn. Incorrectly torqued wheel bearings. Over-tightening or under-tightening wheel bearings during installation can cause vibration. Excessive play or movement. Symptoms: play or movement in the wheel hub when the vehicle is lifted or in motion. Possible causes: worn or loose bearing. A worn bearing can cause excessive play or movement in the wheel hub. Diagnosing axle and bearing problems. Visual inspection. Inspect the axle shafts for visible signs of damage, such as bends, cracks, or dents. Check the wheel bearings for signs of wear, rust, or corrosion. Noise diagnosis. Use the drive test method to help locate the source of the noise. Listen for changes in pitch or intensity as you accelerate, decelerate, or turn the vehicle. Vibration diagnosis. If you notice vibration, check the condition of the axle shafts, bearings, and U-joints. Also, inspect the drive shaft for imbalances. Fluid leak diagnosis. Inspect the axle seals and differential housing for leaks. Use a fluid dye or UV light to help locate the source of the leak if necessary. Removing, replacing, and testing axle assemblies. Removing axle assemblies. Prepare the vehicle. Raise the vehicle using a lift or jack stands. Secure it properly to prevent any movement. Disconnect the battery and remove any components that may obstruct the axle removal. Remove the axle nut. Use a large wrench or impact tool to remove the axle nut. This may require a large amount of torque, depending on the vehicle. Disconnect the suspension components. Remove any suspension components that are in the way of the axle removal. You may also need to remove the driveshaft or other drivetrain components to gain access to the axle. Remove the axle. Once the axle nut and suspension components are removed, carefully slide the axle assembly out of the vehicle. Be mindful of the axle seal and bearing as you remove the assembly. Replacing axle assemblies. Install the new axle. Insert the new axle into the axle housing or differential, ensuring it is properly aligned. Install any seals, gaskets, and bearings that need to be replaced. Ensure that they are installed correctly to prevent leaks. Reconnect suspension components. Reinstall the suspension components that were removed, ensuring that they are securely fastened. Tighten the axle nut to the manufacturer's torque specifications. Check for proper fit and function. Ensure the axle is correctly aligned and that it rotates smoothly without interference. Reinstall the wheels and lower the vehicle to the ground. Testing axle assemblies. Check for leaks. After installation, check for fluid leaks around the axle seals and differential housing. Test drive the vehicle. Take the vehicle for a short test drive to ensure that the axle functions properly, without any abnormal noise or vibration. Check for proper operation. Ensure that the transmission shifts smoothly and that there is no noise or vibration coming from the axle assembly. Conclusion and recap. In this lesson, we covered the diagnostic procedures for axle shaft and bearing problems, including noise, vibration, and leaks. We also provided step-by-step instructions on removing, replacing, and testing axle assemblies. Mastering these procedures is essential for anyone preparing for the ASE certification test and for handling real-world axle and bearing issues in an automotive service environment. Suspension and steering. The suspension system is a vital component in ensuring a vehicle's safety, comfort, and performance. It plays a key role in absorbing shocks from the road, maintaining tire contact with the road surface, and stabilizing the vehicle during turns and maneuvers. This lesson will introduce the fundamental components of suspension systems, such as springs, shock absorbers, and struts, and cover various types of suspension designs, including independent suspension, solid axle, and more. Understanding these elements is crucial for those preparing for the ASE Certification Test A4 and for performing real-world repairs and diagnostics on suspension systems. Components of the suspension system. The suspension system consists of several critical components that work together to absorb road shocks, improve handling, and maintain tire contact with the road surface. These components include springs, shock absorbers, and struts, each of which plays a unique role in the system. Springs. Function of springs. Springs absorb the shock and energy caused by bumps and uneven surfaces on the road. They support the vehicle's weight and allow for controlled movement of the wheels. Types of springs. Leaf springs. Traditionally used in older vehicles and heavy trucks, leaf springs consist of layers of metal that bend to absorb shock. They are particularly effective in supporting heavy loads. Coil springs. The most common type of spring in modern vehicles. Coil springs are wound into a spiral shape and compress or expand to absorb shocks. They are used in both front and rear suspension systems. Torsion bars. Torsion bars work by twisting to absorb shock. They are typically used in the front suspension of trucks and off-road vehicles. Air springs. Air springs are made of rubber and use compressed air to provide suspension. These are typically used in vehicles requiring adjustable ride height or in heavy-duty trucks. How springs work. When a wheel encounters a bump, the spring compresses to absorb the shock. Once the bump is passed, the spring returns to its original shape, helping the wheel stay in contact with the road. Shock absorbers. Function of shock absorbers. Shock absorbers help control the rebound of the springs, ensuring that the wheels stay in contact with the road surface. They convert the kinetic energy created by the springs into heat energy, which is dissipated. Types of shock absorbers. Hydraulic shock absorbers use oil to control movement. As the piston moves through the oil, the shock absorber converts the spring's kinetic energy into heat. Gas shock absorbers. Similar to hydraulic shock absorbers, but use nitrogen gas to pressurize the oil, reducing the chances of foam formation and offering improved performance. Monotube shock absorbers have a single tube for the oil and gas, offering better heat dissipation and consistency in performance. How shock absorbers work. Shock absorbers dampen the motion of the springs by controlling their rebound. Without shock absorbers, the springs would continue to bounce, making the ride unstable. Struts. Function of struts. A strut is a structural component of the suspension system that combines the function of a shock absorber with that of a spring. Struts are designed to support the weight of the vehicle and provide damping. Types of struts. McPherson struts, the most common type used in modern front-wheel drive vehicles. The strut acts as the upper support for the coil spring and provides damping. Twin-tube struts. These are common in heavier-duty applications and provide more strength and durability. How struts work. Struts are typically used in McPherson strut suspension systems, where the strut is mounted directly to the vehicle's body and serves as a structural element of the suspension. They provide both support and shock absorption, improving handling and ride quality. Types of suspension designs. There are various types of suspension systems, each with its advantages and applications. The main difference between suspension designs lies in how the wheels and axles are connected to the vehicle. Independent suspension. Definition. In an independent suspension system, each wheel is connected to the chassis independently, allowing each wheel to move up and down without affecting the other wheel. Advantages. Improved ride comfort, as each wheel can react to the road surface without affecting the opposite wheel. Better handling, particularly in turns, as the wheels can maintain better contact with the road. Common applications. Independent suspension is commonly used in front-wheel drive vehicles and modern passenger cars, where smooth handling and comfort are key priorities. Types of independent suspension. Double wishbone, a suspension design that uses two arms, wishbones, to control the motion of the wheel. It is often used in high-performance cars for better control of wheel alignment. McPherson strut, a simpler independent suspension design using a strut assembly with a coil spring and shock absorber integrated into one unit. Multi-link suspension. This suspension uses multiple arms and links to control wheel movement. It provides excellent handling and comfort, often found in luxury cars. Solid axle suspension. Definition. In a solid axle suspension, both wheels on the same axle are connected by a solid beam, meaning when one wheel moves, the other moves as well. Advantages. Simple and robust design, making it ideal for heavy-duty vehicles. Better towing capacity and load-bearing ability due to the strength of the solid axle. Common applications. Solid axles are commonly found in rear-wheel drive vehicles, pickup trucks, and off-road vehicles, where durability and load-bearing capacity are crucial. Types of solid axle suspension. Leaf spring suspension. Often used in heavy-duty applications, this design uses a series of leaf springs to provide support and absorb shocks. Coil spring suspension. A more modern version of the solid axle, using coil springs instead of leaf springs to improve ride comfort. Torsion bar suspension. Definition. In a torsion bar suspension, the torsion bar acts as a spring, twisting as the vehicle encounters bumps and returning to its original position once the bump is passed. Advantages. Compact design that is used in off-road vehicles and some trucks. Adjustable ride height for specific applications. Common applications. Torsion bar suspensions are typically found in four-wheel drive vehicles, trucks, and military vehicles. Summary of suspension systems. Here's a table showing the summary of suspension systems and how they compare with each other. I'll give you a few minutes to review the table. Conclusion and recap. In this lesson, we covered the fundamentals of suspension systems, including the function and components of springs, shock absorbers, and struts. We also explored the various types of suspension designs, such as independent suspension and solid axle suspension, and discussed their applications in different vehicles. Understanding these concepts is critical for anyone preparing for the ASE Certification Test A4 and for performing suspension repairs in real-world automotive service tasks. Steering system fundamentals. The steering system is a critical component of a vehicle, ensuring that the driver can control the direction of the vehicle efficiently and safely. This lesson covers the key components of the steering system, including steering linkages and power steering systems, as well as common issues such as steering play, noise, and vibration. A solid understanding of these concepts is essential for diagnosing, troubleshooting, and repairing steering system problems, which are crucial skills for those preparing for the ASE certification test. Understanding steering linkage and power steering systems. The steering system includes several key components that work together to ensure the driver can control the direction of the vehicle. These systems may be mechanical or hydraulic, with modern vehicles often using power steering for easier operation. Steering linkage. The steering linkage connects the steering wheel to the wheels, translating the driver's input into wheel movement. It consists of various components that allow the wheels to turn and return to their straight-ahead position. Components of steering linkage. Steering wheel, the part the driver uses to turn the vehicle. It is connected to the steering column. Steering column, the shaft that connects the steering wheel to the steering gear. Steering gear converts the rotational motion of the steering wheel into linear motion, which turns the wheels. Tie rods connect the steering gear to the wheels. Tie rods are essential for adjusting the angle at which the wheels turn. Power steering systems. Power steering uses hydraulic or electric assist to make steering easier for the driver, reducing the effort required to turn the wheel. Types of power steering. Hydraulic power steering uses a hydraulic pump driven by the engine to pressurize fluid that assists in turning the steering gear. The fluid is typically stored in a power steering reservoir. Pump driven by the engine. The pump circulates power steering fluid to the steering gear to provide assist. Hoses and valves carry fluid between the pump and the steering gear, helping direct fluid to the right place. Electric power steering uses an electric motor to assist in turning the steering wheel. It is more energy efficient than hydraulic power steering and requires less maintenance. Motor, a small electric motor mounted on the steering column or rack, providing assistance when the driver turns the wheel. Electronic control unit manages the electric power steering system by monitoring the driver's input and vehicle speed to adjust the steering effort. How power steering systems work. Hydraulic power steering. The hydraulic pump circulates fluid through the system, providing pressure that assists in turning the steering wheel. This reduces the effort required by the driver. Electric power steering. The electric motor is engaged when the steering wheel is turned, providing torque to help the driver turn the wheel with less effort. The ECU adjusts the assistance based on factors like vehicle speed, providing more assistance at lower speeds and less at higher speeds. Common issues in steering systems. Despite their robustness, steering systems can experience several issues over time. The most common problems include steering play, noise, and vibration, each of which can indicate underlying issues that need to be addressed. Steering play. Symptoms: excessive free movement in the steering wheel before the vehicle responds. The driver may notice that turning the steering wheel results in little or no immediate response from the wheels. Possible causes: worn steering linkage components. Worn tie rods, steering rack, or joints can cause play in the steering wheel. Loose steering gear. If the steering gear itself is not securely attached, it can cause excessive movement. Low power steering fluid. Low fluid levels in the power steering system can cause a lack of steering response. Diagnosis: inspect the steering linkage for worn or loose components. Check fluid levels and inspect the steering gear for any signs of damage or excessive play. Steering noise. Symptoms: unusual sounds such as whining, squealing, or grinding when turning the steering wheel. Possible causes: low power steering fluid. Low or dirty fluid can cause whining or groaning sounds from the pump or steering gear. Worn power steering pump. If the power steering pump is damaged or worn out, it may produce whining or grinding noises. Damaged steering components. Worn tie rods, bushings, or bearings can cause noise when turning. Diagnosis: check fluid levels and inspect the pump, hoses, and steering linkage components for wear or leaks. Test the system while the vehicle is idling to pinpoint the source of the noise. Steering vibration. Symptoms: vibration or shaking felt through the steering wheel, particularly when turning or driving at certain speeds. Possible causes: unbalanced wheels. Out-of-balance wheels can cause vibration that is felt in the steering wheel. Worn steering components. Worn steering components such as ball joints, tie rods, or bushings can cause vibration when the steering wheel is turned. Damaged or worn power steering pump. A failing power steering pump can cause vibration, especially at low speeds. Diagnosis: inspect the wheel alignment and balance, check the power steering fluid, and test the steering components for signs of wear or damage. Summary of steering system components and issues. Here's a table below showing the summary of the steering system, including their components and issues. You can pause the video if you want to review the table. Conclusion and recap. In this lesson, we covered the fundamentals of steering systems, including the components and functions of the steering linkage, power steering systems, and common issues such as steering play, noise, and vibration. By understanding these concepts, you will be better equipped to diagnose, troubleshoot, and repair steering system problems, an essential skill for both the ASE Certification Test A4 and real-world automotive repair. Suspension and steering diagnosis. Diagnosing suspension and steering system issues is essential for ensuring that vehicles operate safely and comfortably. This lesson focuses on how to effectively identify and diagnose common suspension and steering system problems, including misalignment issues and handling concerns. A strong understanding of diagnostic techniques for suspension and steering systems is essential for the ASE Certification Test and for real-world automotive diagnostics and repair. Diagnosing suspension and steering system issues. Suspension and steering issues can manifest as a variety of symptoms, from vibrations and noise to handling problems and alignment issues. Proper diagnosis is crucial for repairing these systems effectively. Common suspension issues. Suspension noise. Symptoms: unusual noises, such as clunking, squeaking, or rattling, coming from the suspension system while driving. Possible causes: worn suspension components, worn-out bushings, ball joints, control arms, or sway bar links can cause suspension noise. Damaged shock absorbers. Shock absorbers that are leaking or worn can cause noise, particularly when going over bumps or rough surfaces. Loose or damaged mounting points. If suspension components are not properly mounted, they may move out of alignment and make noise. Diagnostic procedure. Conduct a visual inspection of the suspension components for signs of wear or damage. Test drive the vehicle to isolate the noise, paying attention to whether it occurs while driving, braking, or turning. Listen carefully for any squeaks, clunks, or rattling noises and identify whether they correlate with suspension movement. Suspension vibration. Symptoms: vibration felt through the steering wheel, seat, or floorboards, often at higher speeds or while turning. Possible causes: out-of-balance wheels. Unbalanced wheels or tires can cause vibration, especially at higher speeds. Worn suspension components. Worn suspension bushings, control arms, or sway bars can contribute to vibration. Faulty wheel bearings. Worn wheel bearings can cause vibrations and noise, particularly when turning. Diagnostic procedure. Check wheel balance. Use a balancing machine to check if the wheels are properly balanced. Inspect suspension components. Look for worn or damaged bushings, mounts, or other parts that may cause vibration. Check wheel bearings. Lift the vehicle, check for play in the wheel, and listen for noise while spinning the wheel. Poor handling or reduced ride quality. Symptoms: the vehicle may feel unstable when driving or it may have excessive body roll or diving during turns or braking. Possible causes: worn shock absorbers or struts. These components help control the movement of the vehicle, and when they wear out, the vehicle can feel unstable. Worn springs. Coil springs or leaf springs that have lost their tension may result in poor handling and reduced ride quality. Broken or loose suspension components. Any part of the suspension that is loose or broken will affect handling. Diagnostic procedure. Inspect shock absorbers and struts for leaks, damage, or signs of wear. Test for smooth movement by pushing on the corners of the vehicle and observing the rebound. Check the springs for sagging or deformation. Inspect control arms and sway bars for damage or looseness. Common steering system issues. Steering play. Symptoms: excessive free play in the steering wheel, requiring the driver to turn the wheel significantly before the vehicle begins to respond. Possible causes: worn steering linkage components. Worn tie rods, steering rack, or pitman arm can cause steering play. Loose steering gear. If the steering gear is not properly tightened or is worn out, it can cause play in the wheel. Damaged steering column. Worn or damaged steering column components can also contribute to play in the steering wheel. Diagnostic procedure. Inspect steering linkage for worn or damaged parts, such as tie rods, pitman arm, and idler arm. Check the steering gear for play by moving the steering wheel and observing the response at the wheels. Test the steering column for any loose components. Steering noise, symptoms: a whining, groaning, or squealing sound while turning the steering wheel. Possible causes: low or dirty power steering fluid. If the fluid level is low or the fluid is contaminated, the power steering pump may produce noise. Worn power steering pump. A failing power steering pump can cause whining or groaning sounds when turning. Damaged steering components. Worn steering racks, tie rods, or bushings can cause noise during steering. Diagnostic procedure. Check power steering fluid levels and inspect the fluid condition. If it's low or dirty, flush and replace the fluid. Inspect the power steering pump for signs of wear or failure. Check the steering linkage for worn components or loose parts that could create noise. Hard steering. Symptoms: difficulty turning the steering wheel, particularly at low speeds or when the vehicle is stationary. Possible causes: low power steering fluid. Low fluid levels can cause the steering to become hard or difficult to turn. Failed power steering pump. If the pump fails, there will be no hydraulic assist to make steering easier. Faulty steering rack or gearbox. A worn-out or faulty steering rack or gearbox can make the steering difficult. Diagnostic procedure. Check fluid levels and ensure the power steering fluid is at the correct level. Inspect the power steering pump for proper operation and signs of failure. Test the steering rack for wear or damage and check for leaks. Diagnosing alignment problems. Alignment problems can cause uneven tire wear, poor handling, and steering issues. Proper diagnosis is critical for restoring the vehicle's handling and extending tire life. Common symptoms of alignment issues: uneven tire wear. Tires wear unevenly, with one side wearing faster than the other. Vehicle pulling to one side. The vehicle pulls to the left or right, requiring constant steering correction to drive straight. Steering wheel off-center. The steering wheel may be crooked or off-center when driving straight. Steering drift. The vehicle drifts to one side without any input from the driver. Diagnosing alignment issues. Inspect the tires. Check for uneven wear patterns that may indicate misalignment. Common patterns include wear on the inner or outer edges of the tire, or a cupped pattern. Check the steering wheel. If the steering wheel is off-center, it may indicate that the wheels are misaligned, even if the vehicle drives straight. Perform a test drive. Drive the vehicle and observe if it pulls to one side. A vehicle that drifts or pulls may have a misaligned front end or issues with the steering components. Measure the toe, camber, and caster angles. These angles should be checked with specialized alignment equipment to confirm that the wheels are correctly aligned. Conclusion and recap. In this lesson, we covered the process of diagnosing suspension and steering system issues, including noise, vibration, and handling problems. We also discussed how to diagnose common alignment problems, such as uneven tire wear and steering wheel misalignment. Mastering these diagnostic skills is essential for preparing for the ASE Certification Test A4 and performing effective suspension and steering system brakes. The brake system is one of the most critical safety components in any vehicle. Understanding how brake systems work and how to maintain and repair them is essential for automotive technicians. In this lesson, we will explore the key brake system components, including disc and drum brake systems, as well as the various components such as brake pads, rotors, calipers, and master cylinders. Mastery of these components is crucial for the ASE Certification Test A5 and for diagnosing and repairing brake system problems in the field. Disc and drum brake systems. Brakes are essential for slowing down or stopping a vehicle safely, and disc and drum brake systems are the two main types of braking systems used in most vehicles. Both systems function to convert kinetic energy into heat energy, slowing the vehicle down. However, the components and the way the energy is dissipated differ. Disc brake system. A disc brake system is the most commonly used braking system in modern vehicles, particularly in passenger cars. It consists of several components that work together to slow or stop the vehicle by creating friction against a rotating disc. Components of disc brakes. Brake pads. Made of friction material, the brake pads press against the rotor to create friction and slow down the wheel. Rotors or brake discs. A metal disc that rotates with the wheel. The brake pads press against the rotor to slow the vehicle. Calipers. The caliper holds the brake pads and applies pressure to them, causing them to clamp onto the rotor. Brake fluid. Hydraulic brake fluid is used to transfer pressure from the brake pedal to the caliper. How disc brakes work. When the driver presses the brake pedal, brake fluid is pushed into the calipers, forcing the brake pads against the rotating rotors. This creates friction, which slows the wheel and ultimately stops the vehicle. Drum brake system. Although less common in modern vehicles, drum brakes are still used in some vehicles, especially in rear braking applications. Drum brakes use a different method of creating friction compared to disc brakes, and they have a different design. Components of drum brakes. Brake shoes. The brake shoes press against the inside of the drum to create friction and stop the vehicle. Brake drum. A drum that rotates with the wheel. The brake shoes expand to press against the inside of the drum, creating friction. Wheel cylinder. A hydraulic component that applies pressure to the brake shoes, forcing them against the drum. Brake springs. These springs return the brake shoes to their original position after the brake is released. How drum brakes work. When the brake pedal is pressed, brake fluid is sent to the wheel cylinder, forcing the brake shoes to expand outward and press against the inner surface of the rotating drum. This creates friction, which slows and stops the vehicle. Advantages and disadvantages of drum brakes. Advantages. Drum brakes are more compact and cost-effective. Disadvantages. They tend to overheat more quickly, leading to reduced braking efficiency, and they are less effective than disc brakes at dissipating heat. Key brake system components. Understanding the function of each individual component is key to diagnosing brake issues and performing repairs. Let's take a closer look at the primary components of both disc and drum brake systems. Brake pads. Function. Brake pads are the friction material that presses against the rotors to create the necessary friction for braking. Types of brake pads. Organic. Made of natural materials like rubber, carbon, and Kevlar, organic brake pads are quieter but wear out faster. Semi-metallic. These pads use a mix of metals and other materials, offering better performance and heat dissipation but may be noisier. Ceramic. Made from ceramic compounds, these brake pads are quieter, produce less dust, and have a longer lifespan but can be more expensive. Maintenance. Brake pads should be regularly inspected for wear. If the material is too thin, they should be replaced to avoid damage to the rotor. Rotors or brake discs. Function. The rotors are the circular discs that the brake pads press against to slow the vehicle. Common problems with rotors. Warping. Heat buildup can cause the rotors to warp, leading to vibration when braking. Grooving. Over time, grooves can form on the surface of the rotors due to contact with the brake pads, affecting braking performance. Maintenance. Rotors should be resurfaced or replaced if they are warped or excessively worn. Inspecting the rotor thickness is crucial for determining whether it needs to be replaced. Calipers. Function. The caliper is the part of the brake system that holds the brake pads and applies pressure to them when braking. Types of calipers. Floating calipers. These calipers move horizontally and are used in many vehicles for cost-effectiveness. Fixed calipers. These calipers do not move but instead use multiple pistons to apply force to both sides of the rotor. Common problems with calipers. Seized pistons. Caliper pistons can seize up, preventing the brake pads from properly contacting the rotor. Leaking seals. Leaking seals can cause a loss of brake fluid, leading to decreased braking performance. Master cylinder. Function. The master cylinder is the component that converts the pressure from the brake pedal into hydraulic pressure to engage the brakes. Components of the master cylinder. Reservoir. Stores the brake fluid that is sent to the brake system. Piston. When the brake pedal is pressed, the piston inside the master cylinder forces fluid into the brake lines. Common problems with the master cylinder. Brake fluid leaks. Leaks can occur at the master cylinder seals, reducing brake fluid levels and affecting braking performance. Fading pedal feel. A loss of pressure in the master cylinder can cause the brake pedal to feel soft or spongy. Summary of brake system components. Here's a table showing the summary of brake system components, including their function and common problems. You can pause the video if you want more time to review the table. Conclusion and recap. In this lesson, we explored the components of brake systems, including disc and drum brakes, brake pads, rotors, calipers, and the master cylinder. Understanding how these components work together is essential for diagnosing and repairing braking issues, which is key for the ASE Certification Test A5 and for effective brake system maintenance in a professional environment. Brake system operation. The brake system is a critical component of a vehicle's safety system, ensuring that the vehicle can stop efficiently under various driving conditions. Understanding how brake systems work is essential for diagnosing, maintaining, and repairing these systems. This lesson will focus on the operation of hydraulic braking systems, which are widely used in modern vehicles, and provide a detailed explanation of ABS or anti-lock braking systems, and electronic brake systems, which are increasingly common in advanced vehicle safety systems. How hydraulic braking systems work. Hydraulic braking systems are used in most modern vehicles due to their reliability, efficiency, and effectiveness. The system uses hydraulic force to apply pressure to the brake components, which in turn slows or stops the vehicle. Basic principles of hydraulic brakes. Hydraulic brakes operate on the principle of Pascal's law, which states that pressure applied to an enclosed fluid is transmitted undiminished to all parts of the fluid. This allows a small force applied to the brake pedal to generate a much larger force at the wheels. Components of hydraulic brakes. Master cylinder. The master cylinder converts the force applied to the brake pedal into hydraulic pressure. Brake pedal. When the driver presses the brake pedal, it creates a mechanical force that is transferred to the master cylinder. Brake lines. These are used to transfer brake fluid under pressure from the master cylinder to the brake calipers or wheel cylinders. Brake calipers or wheel cylinders. Calipers apply force to the brake pads in disc brakes, while wheel cylinders apply force to the brake shoes in drum brakes. Brake pads or shoes. These friction materials press against the rotors or drums to create friction and stop the vehicle. Understanding ABS and electronic brake systems. In modern vehicles, anti-lock braking systems, ABS, and electronic brake systems are commonly used to improve safety and braking performance. Anti-lock braking systems, or ABS, is designed to prevent the wheels from locking up during heavy braking, which can cause the vehicle to skid and lose control. By preventing wheel lockup, ABS allows the driver to maintain steering control while braking. How ABS works. When the driver applies the brakes, the ABS system monitors the wheel speed using wheel speed sensors. If the system detects that a wheel is about to lock up, the ABS controller modulates the brake pressure at that wheel by rapidly applying and releasing the brake. This process, known as pulsing the brakes, prevents the wheel from locking while maintaining the braking force. Components of ABS. Wheel speed sensors. These sensors monitor the speed of each wheel and send data to the ABS controller. ABS controller. The controller processes input from the wheel speed sensors and determines when to apply or release brake pressure. Hydraulic valves. These valves are used to adjust the brake pressure during ABS activation. Pump. If necessary, the ABS system uses a pump to restore brake fluid pressure during an ABS event. Electronic brake systems. Electronic brake systems, such as electronic stability control and brake assist, use electronic sensors and controllers to improve braking performance, particularly in emergency situations. How electronic brake systems work. Electronic stability control helps prevent skidding and loss of control by automatically applying the brakes to individual wheels to keep the vehicle on its intended path. Brake assist detects emergency braking and increases braking force to reduce stopping distance. Brake-by-wire systems. Some modern vehicles use electronic sensors and actuators to replace traditional mechanical brake linkages, allowing for more precise control and faster response times. Components of electronic brake systems. Sensors. Sensors are used to monitor the vehicle's stability, wheel speed, and braking force. Electronic control unit. The ECU receives data from the sensors and uses it to control braking force and adjust individual wheel brakes. Actuators. These devices apply braking force to individual wheels in response to the system's commands. Brake-by-wire. This system uses electronic signals instead of hydraulic pressure to operate the brakes, providing faster response times and more precise control. Summary of brake system operation. Here's a table showing the summary of a brake system operation. You can pause the video if you want more time to review the table. Conclusion and recap. In this lesson, we covered the operation of hydraulic braking systems, ABS, and electronic brake systems. We discussed the components that make up these systems, how they function, and the benefits they provide in terms of vehicle safety and braking performance. Understanding these systems is essential for diagnosing and repairing brake-related issues and is a key component of the ASE certification test. Brake diagnosis and repair. Brake systems are essential for vehicle safety, and diagnosing and repairing issues such as brake noise, vibrations, and poor braking performance is a critical skill for any automotive technician. This lesson will guide learners through the process of diagnosing brake noise, vibrations, and performance issues, as well as provide step-by-step instructions for brake fluid checks, bleeding the brake system, and replacing brake components. Mastering these skills is key to preparing for the ASE certification test and for effective brake system repairs in a real-world service environment. Diagnosing brake noise, vibrations, and poor braking performance. Brake issues often manifest through unusual noise, vibration, or reduced braking effectiveness. Identifying these symptoms and diagnosing the underlying causes is essential for effective repair. Diagnosing brake noise. Brake noise can be caused by several factors. Understanding the type of noise can help pinpoint the problem. Squealing or screeching noise. Symptoms: a high-pitched squeal when the brakes are applied, typically occurring when stopping or while driving at lower speeds. Possible causes: worn brake pads. Brake pads that are too thin may cause squealing due to the wear indicators rubbing against the rotor. Contaminated pads or rotors. Dirt, dust, or debris between the brake pads and rotor can lead to squealing. Brake dust. A buildup of brake dust on the pads and rotors can also cause noise. Grinding noise. Symptoms: a loud, metal-on-metal grinding sound, usually indicating severe wear. Possible causes: worn brake pads. When the brake pads wear down to the metal, they make a grinding noise as they contact the rotor. Damaged rotors. grooved or scored rotors from excessive wear or contamination can also cause grinding. Thumping or rubbing noise. Symptoms: a low-frequency thumping or rubbing noise when the vehicle is moving or turning. Possible causes: warped rotors. Rotors that are out of round due to overheating or excessive wear can cause a thumping noise as the brake pads engage with the uneven surface. Worn or damaged calipers. If the calipers are not functioning properly, they may rub against the rotor, creating a thumping sound. Diagnosing brake vibration. Vibrations in the steering wheel or the brake pedal during braking can signal issues with the brake system that need to be addressed. Steering wheel vibration. Symptoms: a vibration felt through the steering wheel, particularly while braking at higher speeds. Possible causes: warped rotors. Warped rotors cause uneven braking force, leading to vibration. Imbalanced wheels. Unbalanced wheels or tires can also cause vibration when braking. Pedal vibration. Symptoms: a pulsating or vibrating brake pedal when the brakes are applied. Possible causes: warped rotors. Warped rotors are the most common cause of pedal vibration, particularly when the brake pads engage the uneven surface of the rotor. Brake fluid contamination. Contaminated brake fluid can cause inconsistent brake performance and vibration. Diagnosing poor braking performance. Poor braking performance, such as the vehicle taking too long to stop or requiring extra effort to brake, can be a sign of underlying issues in the brake system. Symptoms: increased braking distance, soft or spongy brake pedal, uneven braking on one side of the vehicle. Possible causes: low brake fluid. Insufficient brake fluid levels can lead to a soft pedal and reduced braking performance. Air in the brake lines. Air bubbles in the brake lines can cause the brake pedal to feel spongy or unresponsive. Worn brake pads or rotors. Worn pads or rotors can reduce braking efficiency, leading to longer stopping distances. Leaking brake lines or components. Leaks in the hydraulic system can cause loss of brake fluid, reducing braking performance. Brake fluid checks. Bleeding and replacing components. Maintaining proper brake fluid levels and ensuring the system is free from air and contaminants is crucial for optimal brake performance. Additionally, replacing worn components such as brake pads, rotors, and calipers is part of regular brake maintenance. Brake fluid checks. Regular brake fluid checks are essential to ensure the system functions properly and has enough fluid to operate. How to check brake fluid. Locate the brake fluid reservoir. The brake fluid reservoir is usually located near the master cylinder, often at the back of the engine bay. Inspect fluid level. The fluid should be between the min and max lines on the reservoir. If the fluid is low, it may indicate a leak or worn components that need attention. Check fluid condition. Brake fluid should be clear or light amber. If the fluid is dark brown or black, it should be replaced, as it may be contaminated or degraded. Bleeding the brake system. Brake bleeding is necessary when air enters the brake lines or when the brake fluid needs to be replaced. Air in the brake system can result in a spongy or unresponsive brake pedal. How to bleed the brake system. Lift the vehicle. Safely raise the vehicle and remove the wheels. Locate the brake bleed valve. Each brake caliper has a bleed valve located near the top. Use a bleeding kit. Attach a brake bleeding kit to the bleed valve to collect the brake fluid. You will need a helper to press the brake pedal while you open and close the valve. Pump the brake pedal. Have your helper press the brake pedal while you open the bleed valve. Close the valve before your helper releases the pedal. This process should be repeated until all air is removed from the system and clean fluid flows through. Check fluid levels. Make sure the brake fluid reservoir remains full throughout the process to avoid introducing more air into the system. Replacing brake components. Replacing brake pads. Symptoms: worn, noisy, or damaged brake pads can cause poor braking performance and noise. How to replace. Remove the wheel and inspect the pads for thickness. If the pads are worn below the minimum thickness, replace them. Remove the caliper bolts and slide the caliper off the rotor. Remove the old brake pads and insert the new ones, ensuring they are properly aligned. Reinstall the caliper and secure it with the bolts. Replacing brake rotors. Symptoms: warped, grooved, or cracked rotors can cause vibration, noise, and reduced braking performance. How to replace. Remove the wheel and inspect the rotor for damage. If the rotor is worn beyond repair, it must be replaced. Remove the caliper and brake pads from the rotor. Remove any bolts holding the rotor in place and slide the rotor off. Install the new rotor, making sure it is properly seated. Reassemble the brake pads and calipers. Replacing brake calipers. Symptoms: leaking brake fluid, seized calipers, or uneven braking can indicate a problem with the caliper. How to replace. Remove the wheel and caliper assembly from the brake rotor. Disconnect the brake line from the caliper and cap the brake line to prevent fluid leakage. Remove the caliper mounting bolts and remove the caliper. Install the new caliper, reconnect the brake line, and secure the mounting bolts. Conclusion and recap. In this lesson, we covered how to diagnose and repair brake system issues, including brake noise, vibrations, and poor braking performance. We also discussed how to perform brake fluid checks, bleed the brake system, and replace brake components such as pads, rotors, and calipers. Mastering these diagnostic and repair techniques is critical for preparing for the ASE Certification Test A5 and performing effective brake system maintenance in a professional environment. Electrical fundamentals. In modern vehicles, electrical systems play a vital role in almost every function, from starting the engine to powering lights, entertainment systems, and advanced safety features. Understanding the basic principles of electrical circuits, fuses, wiring, power distribution, and battery systems is essential for diagnosing and repairing electrical issues in vehicles. This lesson will provide foundational knowledge of these core elements of automotive electrical systems, laying the groundwork for more advanced topics in electrical diagnostics and repair. An electrical circuit is a pathway through which electricity flows to power various vehicle systems. Understanding how these circuits function is fundamental for diagnosing electrical issues. Basic concepts. Voltage. Voltage, or electrical potential difference, is the force that pushes electric current through a circuit. It is measured in volts. Example: the electrical system in a vehicle operates typically on a 12-volt DC system. Current. Current is the flow of electric charge through the circuit, measured in amperes. It represents the quantity of electricity flowing. Example: a car's starter motor may draw a high current when engaged to start the engine. Resistance. Resistance is the opposition to the flow of current in the circuit, measured in ohms. Higher resistance means less current flow for a given voltage. Example: the resistance of wires and electrical components impacts how much current flows in the circuit. Power. Power is the rate at which electrical energy is used or produced, measured in watts. The formula for electrical power is P equals V times I. Example: an electrical motor might require a certain amount of power to operate, calculated by multiplying the voltage supplied by the current it draws. Ohm's law. Ohm's law is fundamental in understanding how electrical circuits work. It states the relationship between voltage, current, and resistance in a circuit. V equals I times R, where V is voltage, I is current, and R is resistance. By using this formula, you can calculate one of the three variables if you know the other two. Series and parallel circuits. Series circuits. In a series circuit, components are connected end to end, and the current flows through each component. The total resistance is the sum of the individual resistances. Example: the lights in a simple circuit may be wired in series, so if one light goes out, the rest will go out too. Parallel circuits. In a parallel circuit, components are connected across common points, and the current divides between the components. The total resistance is less than the smallest individual resistance. Example: car batteries and electrical components are usually connected in parallel to ensure that if one component fails, others continue to work. Fuses and circuit protection. Fuses are safety devices used to protect electrical circuits from overloads or short circuits. They are designed to blow or melt when the current exceeds a safe limit, preventing further damage to the circuit. Function of fuses. Fuses are essential for preventing overcurrent conditions, which can lead to overheating, fires, or damage to electrical components. How fuses work. Fuses consist of a thin metal wire or filament that melts when the current flowing through it exceeds the rated capacity. When the fuse blows, the circuit is disconnected, preventing further electrical flow. Types of fuses. Blade fuses, these are the most common fuses in automotive electrical systems. They come in various amperage ratings and are used for a wide range of electrical components. Glass tube fuses, these fuses are often found in older vehicles and are typically used in low-current applications. Resettable fuses, these fuses can reset themselves after an overload is cleared, allowing for continued protection without needing to replace the fuse. Fuse ratings. Fuses are rated by their amperage, which corresponds to the amount of current they are designed to carry before blowing. Example: a 15 amp fuse will allow 15 amperes of current to flow through it before it blows. Correct fuse sizing. Always replace a blown fuse with one that has the same amperage rating to prevent overheating and damage to the circuit. Wiring and power distribution. Wiring connects various components of the electrical system and carries the current from one part to another. Proper wiring is essential to ensure safety and prevent system failures. Wiring components. Wires. Wires are the main conductors in a vehicle's electrical system. They come in different gauges depending on the current they are designed to carry. Connectors. Electrical connectors are used to join different parts of the wiring system, ensuring proper electrical contact. Grounding. Proper grounding is essential for safety, as it provides a path for electrical currents to return to the battery and helps prevent electrical shocks. Power distribution. Power is distributed from the battery to various electrical components throughout the vehicle, including lights, sensors, and the engine control module. Proper power distribution ensures that all components receive the appropriate amount of current. Power distribution panel. Modern vehicles have a power distribution panel that controls the flow of electrical power to different circuits. Alternator. The alternator charges the battery and powers the electrical systems while the engine is running. Battery systems. The battery system stores electrical energy and supplies it to the vehicle when the engine is not running. It also stabilizes the voltage and provides current to start the engine. Primary function. The battery stores energy as chemical energy and converts it to electrical energy when needed to start the engine or power electrical systems when the engine is off. Components. Battery cells. A typical car battery has 6 cells, each providing about 2.1 volts, giving a total voltage of around 12.6 volts. Terminals. The battery has positive and negative terminals where cables are connected to the vehicle's electrical system. Electrolyte. A mixture of water and sulfuric acid that facilitates the chemical reaction necessary to produce electrical energy. Battery charging and maintenance. Charging system. The alternator charges the battery while the engine is running. If the alternator fails, the battery will be drained and electrical components will stop working. Battery testing. To ensure the battery is working properly, perform regular voltage tests using a multimeter. A fully charged battery should show around 12.6 to 12.8 volts with the engine off. Summary of electrical system components. Here's a table showing the summary of the different electrical system components, including their function and common problems. You can pause the video if you want more time to review the table. Conclusion and recap. In this lesson, we explored the fundamentals of electrical systems, including hydraulic braking systems, fuses, wiring, power distribution, and battery systems. A solid understanding of these core components is essential for diagnosing, maintaining, and repairing electrical systems in vehicles. and it's critical for preparing for the ASE Certification Test A6. Automotive electrical components. Automotive electrical components are integral to a vehicle's operation, providing power to essential systems like the ignition, lighting, and air conditioning. Alternators, starters, and sensors play key roles in powering the vehicle and ensuring that the systems run smoothly. Understanding the function, common problems, and diagnostic procedures for these components is crucial for anyone preparing for the ASE Certification Test A6. In this lesson, we will explore these key electrical components in detail and cover how to diagnose and repair electrical issues associated with them. Alternators. The alternator is a crucial component of the vehicle's electrical system, responsible for charging the battery and powering the electrical components while the engine is running. Function of the alternator. The primary function of the alternator is to convert mechanical energy from the engine into electrical energy. This electrical energy is used to charge the vehicle battery, power electrical components. How it works. The alternator is driven by the engine's serpentine belt or V-belt, which turns the alternator's rotor. The rotor, which is located inside the stator, creates a magnetic field as it spins. This magnetic field induces electrical current in the stator windings, producing alternating current. The rectifier converts the AC into direct current to charge the battery and power the electrical system. Common alternator problems. No output. Symptoms. The battery light on the dashboard stays illuminated, and the vehicle's electrical systems begin to fail. Possible causes. Failed diodes in the rectifier or voltage regulator. Worn-out alternator brushes. Broken drive belt. Overcharging. Symptoms. The battery fluid may boil, or the dashboard may display an overcharge warning. Possible causes. A faulty voltage regulator that is allowing too much voltage to reach the battery. Incorrect belt tension, which can cause the alternator to operate at an excessively high speed. Noisy alternator. Symptoms. A whining or grinding noise coming from the alternator. Possible causes. Worn bearings or internal parts of the alternator. A loose or misaligned belt. Diagnosing alternator issues. Visual inspection. Check the alternator belt for wear and correct tension. Test voltage. Use a multimeter to measure the battery voltage. A healthy alternator should provide a reading of around 13.8–14.2 volts with the engine running. Test output. Check the alternator output at various engine speeds to see if it provides consistent voltage. Starters. The starter motor is a critical component that initiates the engine's operation by turning the flywheel and beginning the engine's combustion cycle. Function of the starter. The starter motor uses electrical energy from the battery to create the mechanical energy needed to crank the engine. Once the engine begins running, the starter disengages and stops functioning. How it works. When the ignition key is turned or the start button is pressed, current flows from the battery to the starter solenoid, which engages the starter motor. The starter motor turns the flywheel or flex plate, which starts the engine. Once the engine starts, the starter motor disengages from the flywheel. Common starter problems. No crank or start. Symptoms. Turning the key results in no response, or you hear only a clicking sound. Possible causes. A faulty starter motor or solenoid. Weak battery or loose battery connections. Starter grinding noise. Symptoms. A grinding sound when attempting to start the vehicle. Possible causes. Worn-out starter gears or damaged flywheel teeth. Misaligned starter motor. Sticking starter. Symptoms. The starter continues to crank after the engine starts, or it cranks intermittently. Possible causes. Faulty starter solenoid. Electrical issues that cause the solenoid to stay engaged. Diagnosing starter issues. Check battery voltage. Ensure the battery has adequate voltage. Test the starter relay and solenoid. Use a test light to check if the relay or solenoid is receiving power and is functioning correctly. Check for voltage at the starter motor. If there is no voltage at the starter motor, the issue may lie with the solenoid or relay. Sensors. Sensors are vital components in modern vehicles, used to collect data about various engine and vehicle parameters, which are then used by the vehicle's computer to optimize performance and ensure safety. Types of sensors: oxygen sensors. Monitor the oxygen level in the exhaust gases and help control the fuel mixture to improve fuel efficiency and reduce emissions. Crankshaft position sensor. Monitors the position and speed of the crankshaft, helping to synchronize the fuel injection and ignition timing. Throttle position sensor. Measures the position of the throttle valve and helps control the engine's air intake and fuel delivery. Coolant temperature sensor. Monitors the engine's temperature to help the ECU adjust fuel delivery and ignition timing. Mass airflow sensor. Measures the amount of air entering the engine, which helps the ECU calculate the correct amount of fuel for combustion. Common sensor issues: faulty oxygen sensor. Symptoms: poor fuel efficiency, increased emissions, or engine performance issues. Possible causes: worn out or contaminated oxygen sensor. Crankshaft position sensor failure. Symptoms: engine stalling, rough idling, or no start condition. Possible causes: faulty sensor, wiring issues, or electrical faults. Throttle position sensor failure. Symptoms: irregular idle speed, poor acceleration, or engine surging. Possible causes: dirty or worn throttle position sensor. Diagnosing sensor issues. Use a scan tool. Modern vehicles are equipped with an onboard diagnostic system that can read sensor data and report error codes. Test sensor inputs and outputs. Use a multimeter or oscilloscope to measure the voltage or signal output from the sensor. Inspect wiring and connectors. Check for damaged wires, corrosion, or loose connections in the sensor circuit. Summary of automotive electrical components. Here's a table showing the automotive electrical components, including their function and common issues. You can pause the video if you want more time to review the table. Conclusion and recap. In this lesson, we explored the automotive electrical components, including alternators, starters, and sensors, and discussed their roles in the vehicle's electrical system. We also covered common issues related to these components and the procedures for diagnosing and repairing them. Understanding these components is critical for diagnosing electrical issues and performing repairs, which is an essential skill for ASE Certification Test A6. Advanced electrical systems. Modern vehicles rely heavily on electrical systems to operate efficiently and safely. From onboard diagnostics to voltage regulators and charging systems, understanding how to diagnose and repair electrical faults is essential for any automotive technician. This lesson provides a comprehensive overview of advanced electrical systems, including the function and operation of OBD2 systems, voltage regulators, and charging systems, along with fault isolation and repair procedures. Mastering these topics is vital for the ASE certification test and performing effective electrical system repairs in a professional setting. OBD2 systems. The onboard diagnostic system is a critical component in modern vehicles, providing real-time data and enabling technicians to quickly diagnose issues with the vehicle's electrical and mechanical systems. Overview of OBD2. OBD2 is a standardized system that monitors and reports on various vehicle subsystems, including the engine, transmission, exhaust, and more. It provides a way for technicians to access detailed information about the vehicle's performance and troubleshoot problems using an OBD2 scanner. Components of the OBD2 system: vehicle control module, the central computer that controls various vehicle systems and stores diagnostic trouble codes. Sensors. Sensors placed throughout the vehicle monitor engine performance, emissions, and other parameters. Data link connector. The port where an OBD2 scanner is plugged in to access vehicle data and read trouble codes. Reading and interpreting trouble codes. When a fault is detected, the OBD2 system generates a diagnostic trouble code, which helps technicians pinpoint the problem. These codes are categorized by the first digit, which denotes the type of system the code refers to. P codes, powertrain issues. B codes, body-related issues. C codes, chassis-related issues, U-codes, network and communication issues. How to use an OBD2 scanner. Connect the OBD2 scanner to the DLC under the dashboard. Follow the scanner's instructions to read and clear trouble codes. Use the code data to identify the system or component at fault. Common OBD2 troubleshooting codes: P0300, random misfire detected; P0420, catalyst system efficiency below threshold; P0171, fuel trim system lean; P0600, serial communication link malfunction. These codes can point to specific issues that can be diagnosed further using manufacturer service manuals and diagnostic procedures. Voltage regulators and charging systems. The voltage regulator and charging system are responsible for maintaining the proper voltage and charging the vehicle's battery while the engine is running. Function of the charging system. The charging system's primary job is to provide electrical power to the vehicle's systems and to recharge the battery when it is drained by vehicle operations. Alternator. The alternator generates AC and sends it to the voltage regulator, which converts the AC to DC and regulates the amount of voltage sent to the battery. Battery. The battery stores electrical energy to power the vehicle when the engine is off, supplying power to start the engine and run electrical systems like lights and the radio. Voltage regulator function. The voltage regulator ensures the alternator provides the correct voltage. If the voltage is too high, it can damage the battery and other electrical components. If the voltage is too low, the battery won't charge properly, and electrical components won't function as expected. Types of voltage regulators. Internal regulator. Most modern vehicles have an internal voltage regulator built into the alternator. External regulator. Older vehicles use an external regulator mounted separately from the alternator. Diagnosing charging system problems. Check the battery voltage. Use a multimeter to check the battery voltage. A healthy system should provide between 13.8 and 14.2 volts when the engine is running. Test the alternator output. Use an alternator tester or a multimeter to test the alternator's output. The voltage should remain steady as the engine revs. Check the voltage regulator. If the alternator output is too high or too low, the voltage regulator may need to be replaced. Electrical system fault isolation and repair. Electrical issues in vehicles can be complex, requiring advanced diagnostic skills to isolate and fix. Effective fault isolation involves using proper diagnostic equipment and techniques to find the root cause of the issue. Common electrical system issues. Blown fuses. Symptoms. Electrical components or systems stop working. Diagnosis. Inspect fuses and replace any that are blown. Use a fuse tester to check for continuity. Short circuits. Symptoms. The vehicle experiences sudden loss of power, or there is a burning smell from wiring. Diagnosis. Visually inspect wiring for damage or exposed wires. Use a multimeter to check for continuity in the circuit. Faulty grounding. Symptoms. Electrical components malfunction or fail to work. Diagnosis. Inspect grounding points and wiring connections. Clean or repair any loose or corroded grounds. Damaged wiring. Symptoms. Intermittent power loss or malfunctioning electrical components. Diagnosis. Use a wire tracer or multimeter to check for continuity and locate damaged wires. Diagnostic procedures. Use a multimeter. Measure voltage, current, and resistance in various electrical components. This can help identify issues such as a weak battery, damaged alternator, or faulty sensor. Use an OBD2 scanner. If the issue is related to sensors or control systems, use an OBD2 scanner to read trouble codes and sensor data. Perform continuity tests. For wiring and electrical components, continuity tests can help identify breaks in the circuit. Check for voltage drops. A voltage drop test can help diagnose high-resistance connections in the electrical system, which can lead to poor performance or component failure. Summary of advanced electrical systems components. Here's a table showing the advanced electrical systems components, including their function and common issues. You can pause the video if you want more time to review the table. Conclusion and recap. In this lesson, we covered advanced electrical systems in vehicles, including OBD2 systems, alternators, voltage regulators, and charging systems. We also discussed common electrical issues, diagnostic procedures, and repair techniques. Mastering these topics is critical for effectively diagnosing and repairing electrical issues and essential for the ASE Certification Test A6. HVAC system components. The heating, ventilation, and air conditioning, or HVAC system in a vehicle is responsible for regulating the cabin temperature, controlling air quality, and ensuring proper ventilation. Understanding how the HVAC system works and the role of its components, such as refrigerants, compressors, condensers, and evaporators, is essential for diagnosing, maintaining, and repairing climate control systems. This lesson will provide learners with a comprehensive understanding of HVAC systems and their components, forming a solid foundation for anyone preparing for the ASE Certification Test A7. Understanding heating, ventilation, and air conditioning systems. HVAC systems are integral to maintaining a comfortable and safe environment inside the vehicle. They regulate the temperature, humidity, and air quality, improving passenger comfort and ensuring defogging and defrosting in adverse weather conditions. Purpose of HVAC systems. Heating. The heating system warms the cabin, using the engine's heat to provide warmth. It also prevents frost buildup on the windows by using the defrost function. Ventilation. This system circulates air inside the vehicle, ensuring that fresh air is supplied and stale air is exhausted. Air conditioning. The AC system cools the cabin air, reducing temperature and humidity, often through the use of a refrigerant. It's vital for comfort during warm weather conditions. HVAC system operation. The HVAC system is powered by the vehicle's engine, with an electric blower motor circulating air through the system. The operation of the system can be summarized as follows. Heating. The heater core receives hot coolant from the engine and circulates it through the vehicle cabin to raise the interior temperature. Ventilation. A blower motor pushes air from outside or recirculated air through the vents into the cabin. Air conditioning. The compressor pressurizes refrigerant and sends it to the condenser, where it is cooled. The refrigerant is then evaporated in the evaporator, absorbing heat from the cabin and cooling the air. Key HVAC components. There are several key components in an HVAC system that work together to regulate the temperature and air quality inside the vehicle. Refrigerants. Refrigerants are chemicals used in the air conditioning system to absorb and release heat efficiently. They circulate through the system, changing states from gas to liquid and back. Function. Refrigerants absorb heat from the cabin air and release it outside, providing a cooling effect. Common refrigerants. R134A. The most commonly used refrigerant in vehicles before 2020. R1234YF. A more environmentally friendly alternative used in newer vehicles. Regulations. The use of certain refrigerants is regulated due to their environmental impact, particularly their role in ozone depletion and global warming potential. Compressors. The compressor is the heart of the air conditioning system. It compresses the refrigerant gas to a high pressure, turning it into a hot, high-pressure liquid. Function. The compressor pressurizes the refrigerant, sending it through the condenser to release heat. The compressor is usually driven by a belt connected to the engine's crankshaft. Types of compressors. Reciprocating compressors. Use a piston to compress refrigerant, commonly found in older systems. Scroll compressors. Use a pair of interleave scrolls to compress refrigerant, providing higher efficiency and smoother operation. Common problems. Compressor failure, caused by a lack of lubrication, electrical failure, or worn-out parts. Low refrigerant levels can cause the compressor to overheat or seize. Condensers. The condenser is a heat exchanger that cools the high-pressure refrigerant gas, turning it back into a liquid state. This is the component that releases the heat absorbed by the refrigerant in the cabin. Function. The condenser receives the high-pressure refrigerant from the compressor and uses airflow to cool the gas, turning it into a high-pressure liquid. Location. The condenser is typically located at the front of the vehicle, in front of the radiator, where it can be cooled by the incoming air. Common problems: clogged condenser, dirt, debris, or refrigerant leaks can clog the condenser and reduce its efficiency. Leaks. Leaks in the condenser can cause refrigerant loss, reducing the system's cooling capability. Evaporators. The evaporator is the component responsible for absorbing heat from the cabin air and cooling the air as it passes over it. It's typically located inside the vehicle's dashboard. Function. As refrigerant enters the evaporator, it expands and evaporates, absorbing heat from the air inside the cabin and lowering the temperature. Common problems: clogged evaporator. Dirt, dust, and mold can accumulate in the evaporator, reducing its efficiency and causing unpleasant odors. Frozen evaporator. Low refrigerant or restricted airflow can cause the evaporator to freeze, hindering the air conditioning system. Diagnosing HVAC system issues. Diagnosing HVAC issues involves understanding how the system works and identifying symptoms based on vehicle behavior. Below are common problems and diagnostic techniques. Common HVAC system problems: no cool air. Possible causes: low refrigerant levels, compressor failure, or malfunctioning condenser. Diagnosis: check refrigerant levels with a pressure gauge, inspect the compressor and condenser, and look for any visible leaks. Warm air blowing from the air conditioning. Possible causes: faulty expansion valve, low refrigerant, or a failed compressor. Diagnosis: measure refrigerant pressures, check compressor operation, and inspect the expansion valve for blockages. No airflow or weak airflow. Possible causes: a clogged cabin air filter, faulty blower motor, or defective fan control switch. Diagnosis: inspect the cabin air filter, test the blower motor, and check the fan settings. Unpleasant odors. Possible causes: mold or bacteria buildup in the evaporator. Diagnosis: inspect the evaporator for signs of mold and clean or replace as necessary. Troubleshooting techniques. Pressure tests. Use refrigerant pressure gauges to check for proper refrigerant levels and system pressure. Electrical testing. Use a multimeter to check for power issues in the blower motor, compressor, and sensors. Visual inspections. Look for leaks in the refrigerant lines, cracks in hoses, or signs of wear on components such as the condenser and evaporator. Summary of HVAC system components. Here's a table showing the different HVAC system components, including their function and common problems. You can pause the video if you want more time to review the table. Conclusion and recap. In this lesson, we explored the components of HVAC systems, including refrigerants, compressors, condensers, and evaporators, and discussed how they work together to regulate temperature and air quality in the vehicle. We also covered common problems that can occur within the HVAC system and the procedures for diagnosing and troubleshooting these issues. Air conditioning diagnosis. Diagnosing air conditioning issues is an essential skill for automotive technicians. Air conditioning systems are complex, consisting of multiple components like the compressor, condenser, evaporator, and refrigerant lines. This lesson will provide an in-depth understanding of how to diagnose common AC problems such as low refrigerant, electrical issues, and poor cooling performance. Additionally, we will cover techniques for performing cooling performance tests and using advanced diagnostic tools for leak detection. Mastery of these diagnostic techniques is key for ASE Certification Test A7 and ensuring the proper function of vehicle air conditioning systems. Diagnosing AC issues: low refrigerant, electrical problems, and cooling performance. Air conditioning issues can stem from a variety of causes. Understanding how to diagnose these problems accurately is crucial for effective repairs. Low refrigerant. Low refrigerant levels are one of the most common causes of poor cooling performance in AC systems. When the refrigerant is low, the system cannot properly absorb and release heat, leading to insufficient cooling. Symptoms: poor cooling performance, ice or frost formation on the evaporator coil, no cold air or intermittent cold air. Causes of low refrigerant: refrigerant leaks, Leaks in hoses, seals, or components, such as the evaporator or condenser, can lead to refrigerant loss. Evaporator coil icing. Low refrigerant can cause the evaporator coil to freeze up, blocking airflow and further reducing cooling efficiency. Diagnosis. Visual inspection. Inspect all AC system components for signs of refrigerant leakage. Refrigerant gauge test. Connect a refrigerant gauge to the low pressure side of the system. Low pressure readings can indicate low refrigerant levels. Temperature test. Use a thermometer to measure the temperature of the air entering and exiting the evaporator. A significant difference suggests that the refrigerant is functioning properly. Solution. If refrigerant levels are low, locate and repair any leaks and then recharge the system to the correct refrigerant level. Electrical problems. Electrical problems can affect several components of the AC system, including the compressor, condenser fan, and blower motor. Faulty electrical connections can lead to intermittent or complete system failure. Symptoms. The AC system does not turn on. The compressor is not engaging. The blower motor does not function properly. Common electrical issues. Blown fuses. A blown fuse can prevent the system from operating. Faulty compressor clutch. The clutch engages and disengages the compressor. If it fails, the compressor will not function. Worn-out blower motor. A damaged blower motor can lead to weak or no airflow. Diagnosis. Check the fuse. Inspect the AC system fuse for continuity. Replace if blown. Test compressor clutch. Use a multimeter to check the continuity of the compressor clutch circuit. If there is no continuity, the clutch may be faulty. Check the blower motor. Test the blower motor with a multimeter for voltage. If the motor is not receiving voltage, check for issues in the control circuit. Solution. Replace or repair faulty components, including fuses, compressor clutch, or blower motor as necessary. Poor cooling performance. Sometimes the AC system may run but fail to cool the cabin effectively. This could be caused by several issues beyond just low refrigerant levels. Symptoms. The AC blows air, but it is not cold enough. Inconsistent cooling. Cold air only at higher RPM. Possible causes. Clogged or dirty air filter. A clogged cabin air filter can restrict airflow, reducing the effectiveness of the AC. Blocked condenser. A blocked condenser reduces the ability to release heat from the refrigerant, leading to poor cooling. Faulty expansion valve. If the expansion valve is not functioning correctly, it can cause the refrigerant to expand too much or too little, affecting cooling performance. Diagnosis. Check cabin air filter. Inspect and replace the cabin air filter if it is clogged or dirty. Inspect the condenser. Check the condenser for dirt, debris, or damage. Clean or replace as necessary. Check expansion valve. Test the expansion valve to ensure it is regulating refrigerant flow properly. Solution. Clean or replace the cabin air filter. Clear any debris from the condenser, and repair or replace faulty expansion valves. Cooling performance tests and leak detection. Accurately diagnosing AC system issues requires the use of specific diagnostic tools and techniques to measure system performance and detect leaks. Cooling performance tests. Cooling performance tests help determine whether the AC system is working within optimal parameters. These tests focus on the temperature differential and pressure readings. Temperature differential test. Measure the air temperature coming from the AC vents and compare it to the ambient air temperature. A properly functioning system should produce air that is 20 to 30 degrees Fahrenheit cooler than the outside temperature. Pressure gauge test. Attach a refrigerant gauge to the low and high pressure sides of the system. Compare the readings to the manufacturer's specifications to determine if the system is operating within normal pressure ranges. Leak detection. Finding refrigerant leaks is crucial for restoring system performance. Leaks can occur at various points in the system, including hoses, seals, and fittings. Visual inspection. Look for oily spots, stains, or wetness around seals, fittings, and hoses that could indicate a refrigerant leak. UV dye leak detection. Introduce UV dye into the AC system. Use a UV light to inspect the system. Leaks will fluoresce under the UV light, revealing their location. Electronic leak detector. An electronic leak detector can be used to sense the presence of refrigerant in the air around the system. Move the detector around hoses, fittings, and other possible leak points to identify refrigerant escaping. Bubble solution test. Apply a soapy solution to the suspect area. If bubbles form, it indicates a leak in the system. Summary of air conditioning diagnosis. Here's a table showing the summary of air conditioning diagnosis. You can pause the video if you want more time to review the table. Conclusion and recap. In this lesson, we covered the diagnostic techniques for air conditioning system issues, including low refrigerant, electrical problems, and poor cooling performance. We also discussed how to conduct cooling performance tests and how to identify refrigerant leaks using tools like UV dye and electronic leak detectors. Mastering these diagnostic procedures is essential for effective repairs and for preparing for the ASE Certification Test A7. Heating systems. The heating system in a vehicle is essential for maintaining comfort in cold weather conditions. The system relies on the heat produced by the engine and circulates it through the cabin. Diagnosing and repairing heating system malfunctions, such as issues with the heater core, is a critical skill for automotive technicians. In this lesson, we will cover the diagnostic steps for identifying heating system issues, including common symptoms of heater core problems, and the procedures for effective repairs. Diagnosing heating system malfunctions. Heating system issues can arise from various components, such as the heater core, blowers, and controls. Being able to diagnose these problems efficiently is essential for effective repairs. Common symptoms of heating system malfunctions. No heat. Symptoms. The vehicle's heater blows cold air or there is no airflow. Possible causes. Low coolant levels. Insufficient coolant prevents the heater core from transferring heat. Faulty thermostat. If the thermostat is stuck open, the engine may not reach the proper operating temperature, preventing the heating system from working. Blower motor issues. If the blower motor is malfunctioning, there may be no airflow through the heating system. Insufficient heat. Symptoms. The heater blows warm air but not hot enough to warm the cabin. Possible causes. Partially clogged heater core. A partially blocked heater core reduces heat transfer, causing lukewarm air to blow from the vents. Faulty or improperly adjusted thermostat. A thermostat that's stuck partially open can cause insufficient engine heating. Unpleasant odors. Symptoms. A musty or burning smell coming from the heater vents. Possible causes. Mold or debris in the HVAC system. Moisture inside the heater core or ducts can cause mold or mildew growth. Overheating coolant. Overheating coolant can emit a burnt smell when it enters the cabin through the heater vents. Leaking coolant. Symptoms. A puddle of coolant under the dashboard or an unusual sweet smell inside the vehicle. Possible causes. Leaking heater core. A leaking heater core can allow coolant to spill inside the vehicle, often resulting in a sweet smell and coolant puddles. Diagnostic steps for heating system malfunctions. Visual inspection. Check for leaks in the coolant system, including the heater core and hoses. Inspect the blower motor and related components to ensure proper operation. Check coolant levels. Low coolant levels can prevent the heater core from working effectively. Ensure that coolant is at the proper level in the radiator and overflow tank. Test the thermostat. A faulty thermostat can prevent the engine from heating up properly, affecting the heating system. Test the thermostat by observing the temperature gauge to see if it is reaching the normal operating temperature. Check the blower motor. If there's no air coming from the vents, test the blower motor by ensuring it is receiving power. If the motor is faulty, it will need to be replaced. Check for leaks in the heater core. A leaking heater core will cause coolant to enter the cabin. If coolant is leaking, the heater core must be replaced. Heater, core problems and repairs. The heater core is a crucial component in the vehicle's heating system. It works by transferring heat from the engine coolant to the cabin air. Common heater core problems. Clogged heater core. Symptoms. Insufficient heating with only lukewarm air blowing from the vents. Causes. Over time, debris and contaminants can accumulate inside the heater core, reducing its ability to transfer heat. Leaking heater core. Symptoms: sweet-smelling coolant inside the cabin, wet carpet, or foggy windows. Causes: corrosion or physical damage can cause the heater core to leak coolant inside the vehicle. Air in the heater core. Symptoms: inconsistent heating or cold spots in the cabin. Causes: air trapped in the heater core can prevent proper coolant flow, resulting in reduced heating performance. Diagnosing heater core issues. Coolant leaks. Look for signs of coolant on the floor of the passenger compartment or damp carpets. A leaking heater core will often result in coolant puddles inside the vehicle. Coolant temperature. Monitor the coolant temperature with a gauge or thermometer. If the temperature is too low, it could indicate that the coolant is not circulating properly through the heater core. Heater core flush. Perform a flush on the heater core to clear any blockages or debris that could be preventing proper airflow and heat transfer. Heater core repair or replacement. Heater core flush. To remove debris or buildup in the heater core, use a flush kit and clean water or a specialized cleaner to flush the system. If this does not improve performance, further disassembly is required to clean the core more thoroughly or replace it. Replacing a heater core. Replacing a heater core is typically more complex and involves removing parts of the dashboard or interior trim to access the core. Steps for replacement. Step 1. Disconnect the battery to prevent electrical shock. Step 2. Drain the coolant from the radiator and hoses. Step 3. Remove the dashboard components and any obstruction to access the heater core. Step 4. Disconnect the hoses and remove the heater core. Step 5. Install the new heater core, ensuring proper seal and alignment. Step 6. Reinstall the dashboard components and reconnect the hoses. Step 7. Refill the system with coolant and check for leaks. Summary of heating system diagnosis and repair. Here's a table showing the summary of heating system diagnosis and repair, including their symptoms, common causes, and how to diagnose and repair them. You can pause the video if you want more time to review the table. Conclusion and recap. In this lesson, we covered how to diagnose and repair heating system malfunctions, including issues with the heater core, thermostat, and blower motor. We also discussed how to diagnose problems such as insufficient heat, coolant leaks, and unpleasant odors, and provided steps for repairing or replacing faulty components. Mastery of these skills is essential for the ASE Certification Test A7 and for effective HVAC system repairs in a professional environment. Engine control systems. Engine performance is critical for vehicle efficiency, fuel economy, and overall engine longevity. The engine control systems are responsible for monitoring and managing key components that directly impact engine performance. These include the fuel injection system, ignition system, sensors, and the engine control module. Understanding how each of these components works, how they interact, and how to diagnose issues is key to maintaining optimal engine performance. This lesson will dive into each of these systems, providing foundational knowledge to help you effectively diagnose and troubleshoot engine performance problems. Fuel injection systems. Fuel injection is a critical component in modern engines, replacing carburetors to deliver precise amounts of fuel to the engine cylinders. The fuel injection system works in tandem with the engine control module to optimize fuel delivery based on various engine conditions. Function of fuel injection. Fuel injection systems are responsible for mixing fuel with air in precise amounts to allow for efficient combustion. The engine's ECM controls fuel delivery based on inputs from various sensors. Types of fuel injection systems. Single-point fuel injection. Fuel is injected into the intake manifold near the throttle body, where it mixes with air before entering the cylinders. Multi-point fuel injection. Each cylinder has its own fuel injector that directly injects fuel into the intake manifold, providing more precise fuel control. Direct injection. Fuel is injected directly into the combustion chamber, allowing for more efficient combustion and better fuel economy. Key components of fuel injection systems. Fuel injectors. The injectors are responsible for delivering fuel to the engine in a precise spray pattern. These are controlled by the ECM, which regulates the timing and duration of the injection. Fuel pump. The fuel pump supplies fuel from the fuel tank to the fuel injectors under pressure. Fuel pressure regulator. This component maintains the fuel pressure within the system to ensure consistent fuel delivery. Fuel filter. The fuel filter removes impurities from the fuel to prevent clogging of the fuel injectors, diagnosing fuel injection system issues. Symptom: engine misfire or rough idle. Possible causes: clogged or faulty fuel injectors, low fuel pressure, faulty fuel pump. Diagnosis: perform a fuel pressure test to check for proper fuel delivery. Inspect fuel injectors for clogging and use a Noid light to test injector operation. Symptom: poor fuel economy. Possible causes: faulty fuel pressure regulator, malfunctioning sensors, or improper fuel mixture. Diagnosis: check the oxygen sensors, mass airflow sensor, and fuel pressure regulator to ensure the engine is receiving the correct fuel-air ratio. Ignition systems. The ignition system provides the spark necessary to ignite the fuel-air mixture in the combustion chamber. The system includes components such as spark plugs, ignition coils, and the ignition control module. Function of the ignition system. The ignition system ensures that the engine's spark plugs fire at the correct time to initiate combustion. It must provide enough energy to create a spark that can ignite the air-fuel mixture, ensuring that the engine runs smoothly. Key components of the ignition system. Ignition coil converts low voltage from the battery into high voltage that is sent to the spark plugs. Distributor. In older systems, the distributor directs high voltage to the correct spark plug. In modern systems, this function is often replaced by individual coils for each cylinder. Spark plugs. Spark plugs create the spark that ignites the air-fuel mixture in the engine cylinders. Ignition control module. The control module regulates the timing of spark generation based on inputs from sensors such as the crankshaft position sensor. Diagnosing ignition system issues. Symptom: engine misfire. Possible causes: faulty spark plugs, malfunctioning ignition coils, or a bad ignition control module. Diagnosis: inspect spark plugs for wear or carbon buildup. Use a spark tester to check for spark at the plug. Test ignition coils and the ignition control module for proper function. Symptom: hard starting or no start. Possible causes: weak spark, faulty ignition coil, or broken timing chain. Diagnosis: test the ignition coil for continuity using an ohm meter. Check the timing with a timing light and inspect the timing chain for wear. Sensors and ECM. The engine control module is the brain of the engine, using data from various sensors to control the operation of the fuel injection and ignition systems. The sensors collect real-time data on engine performance, which the ECM uses to make adjustments that optimize fuel efficiency, performance, and emissions. Types of sensors in the engine control system. Crankshaft position sensor monitors the position and speed of the crankshaft to determine the timing of fuel injection and spark. Camshaft position sensor works in conjunction with the crankshaft position sensor to determine the position of the camshaft, which helps with fuel and ignition timing. Oxygen sensors monitor the exhaust gases to ensure the air-fuel ratio is optimal for combustion. They send data to the ECM to adjust fuel delivery. Mass airflow sensor measures the amount of air entering the engine to help the ECM calculate the correct amount of fuel for combustion. Coolant temperature sensor monitors engine temperature and helps the ECM regulate fuel injection timing and air-fuel mixture. Engine control module. The ECM processes data from all of the sensors and controls components like the fuel injectors, ignition system, and exhaust system. How it works. The ECM adjusts various parameters to ensure optimal engine performance, including fuel mixture, ignition timing, and idle speed. Diagnostics. The ECM stores diagnostic trouble codes when it detects malfunctions. These codes can be retrieved using an OBD2 scanner, which helps technicians pinpoint problems in the engine control system. Diagnosing sensor and ECM issues. Symptom: engine running rich or lean. Possible causes: faulty oxygen sensor, mass airflow sensor, or coolant temperature sensor. Diagnosis: use a scan tool to retrieve DTCs from the ECM and check for sensor malfunctions. Perform voltage tests on the sensors to ensure proper operation. Symptom: engine stalling or poor idle. Possible causes: malfunctioning crankshaft position sensor or camshaft position sensor. Diagnosis: inspect and test the sensors using a multimeter to check for proper signal output. Verify the ECM is receiving accurate data from these sensors. Summary of engine control systems. Here's a table showing the summary of engine control systems. You can pause the video if you want more time to review the table. Conclusion and recap. In this lesson, we explored engine control systems, including the operation of fuel injection, ignition, and sensors, and the role of the engine control module. We also discussed common issues related to these systems and diagnostic steps to resolve them. A strong understanding of these systems is essential for troubleshooting engine performance issues and is critical for ASE Certification Test A8. Engine diagnostics. Diagnosing engine performance issues is a key skill for automotive technicians. Engine problems like misfires, poor fuel economy, and general performance issues can be caused by a wide range of factors, from faulty sensors to worn-out components. This lesson will cover the diagnostic techniques used to identify and resolve common engine problems. Additionally, learners will be introduced to the tools required for in-depth engine performance analysis, such as OBD2 scanners, multimeters, and oscilloscopes. Diagnosing engine misfires. An engine misfire occurs when one or more cylinders fail to fire properly, causing the engine to run unevenly. Misfires can lead to poor engine performance, reduced fuel efficiency, and increased emissions. Symptoms of engine misfire. Rough idling. The engine may shake or vibrate when idling. Loss of power. Acceleration may be sluggish or uneven. Check engine light. The check engine light will typically illuminate, often accompanied by a misfire-related DTC. Increased emissions. Misfires lead to incomplete combustion, increasing exhaust emissions. Common causes of engine misfires. Ignition system issues. Faulty spark plugs or ignition coils can prevent proper ignition in the cylinders, leading to misfires. Worn-out spark plug wires or poor connections can also cause misfires by disrupting the ignition spark. Fuel system problems. Clogged fuel injectors or a faulty fuel pressure regulator can result in insufficient fuel delivery, causing misfires. Low fuel pressure due to a failing fuel pump or clogged fuel filter can lead to improper combustion. Air intake issues. Vacuum leaks or a dirty air filter can cause the air-fuel mixture to be off balance, leading to misfires. Faulty mass airflow sensor can misinterpret the air intake, leading to incorrect fuel delivery. Engine compression problems. Low compression in the engine cylinders due to worn piston rings, valve seals, or gasket failures can cause misfires. Diagnosing engine misfires. Check engine light and codes. Use an OBD2 scanner to read the trouble codes stored in the vehicle's computer. Common misfire codes include P0300 and specific codes for individual cylinders. Spark test. Use a spark tester to check the spark at each spark plug. If a spark is absent, the issue may lie in the ignition system. Fuel system test. Use a fuel pressure gauge to check if the fuel system is delivering the correct amount of fuel. Also, check for proper fuel injector operation using an injector pulse tester. Compression test. Perform a compression test to check for engine cylinder health. Low compression may indicate internal engine damage. Diagnosing poor fuel economy. Poor fuel economy is often a symptom of inefficient engine performance. A variety of factors, from fuel delivery issues to sensor malfunctions, can cause a vehicle to consume more fuel than usual. Symptoms of poor fuel economy. Reduced miles per gallon. The vehicle requires more fuel to travel the same distance. Poor acceleration. reduced throttle response may indicate the engine is not operating efficiently. Increased exhaust emissions. Excess fuel that does not combust properly leads to higher exhaust emissions. Common causes of poor fuel economy. Faulty oxygen sensors. Oxygen sensors monitor the exhaust gases and send feedback to the Engine Control Module, ECM, to adjust the fuel-air mixture. A faulty sensor can lead to an incorrect fuel mixture, causing poor fuel economy. Dirty air filter. A clogged or dirty air filter reduces airflow to the engine, causing the engine to work harder and consume more fuel. Fuel injector issues. Clogged or malfunctioning fuel injectors can cause uneven fuel distribution, leading to poor fuel economy. Low tire pressure. Low tire pressure increases rolling resistance, causing the engine to work harder and use more fuel. Driving habits. Aggressive driving, such as rapid acceleration and heavy braking, can drastically reduce fuel efficiency. Diagnosing poor fuel economy. Check OBD2 codes. Use a scanner to check for any codes related to the fuel system, oxygen sensors, or air-fuel mixture. Inspect the air filter. Replace a clogged air filter to ensure optimal airflow to the engine. Test fuel injectors. Inspect fuel injectors for proper operation using an injector pulse tester and ensure there are no blockages or leaks. Check tire pressure. Ensure that the tires are inflated to the correct pressure. Underinflated tires can lead to poor fuel economy. Using diagnostic tools for engine performance analysis. Effective diagnosis of engine performance issues requires a variety of diagnostic tools. These tools help technicians identify problems with the fuel, ignition, and air intake systems. OBD2 scanner. The OBD2 scanner is essential for reading diagnostic trouble codes and monitoring real-time engine data from the ECM. How to use. Plug the OBD2 scanner into the OBD2 port under the dashboard. Turn on the ignition and retrieve stored trouble codes. Analyze the data for misfires, fuel mixture problems, and sensor malfunctions. Multimeter. A multimeter is used to test the electrical components of the engine control systems, such as ignition coils, fuel injectors, and sensors. How to use. Set the multimeter to measure voltage, resistance, or current as needed. Test components such as spark plugs, coil resistance, and sensor signals for proper function. Fuel pressure gauge. A fuel pressure gauge is used to measure the pressure within the fuel system, ensuring that the fuel injectors are receiving the correct pressure. How to use. Attach the gauge to the fuel rail or test port on the fuel system. Start the engine and observe the fuel pressure reading. Compare the reading to manufacturer specifications. Low or high fuel pressure can indicate issues with the fuel pump or pressure regulator. Compression tester. The compression tester is used to assess the health of the engine's cylinders by measuring the pressure they produce during cranking. How to use. Remove the spark plug from the cylinder to be tested. Screw the compression tester into the spark plug hole. Crank the engine and record the pressure reading. Low compression readings indicate potential issues such as worn-out pistons, rings, or valves. Summary of engine diagnostics tools and techniques. Here's a table showing the Summary of Engine Diagnostics Tools and Techniques, including their purpose and techniques. You can pause the video if you want more time to review the table. Conclusion and recap. In this lesson, we covered how to diagnose engine misfires, poor fuel economy, and other performance issues using OBD2 scanners, multimeters, fuel pressure gauges, and compression testers. We also explored common causes of these issues and discussed how to use diagnostic tools effectively. Mastering these techniques is essential for diagnosing engine performance issues, emission control systems. In today's automotive industry, emission control systems play a vital role in reducing harmful pollutants released by vehicles into the atmosphere. These systems include components such as catalytic converters, oxygen sensors, and exhaust gas recirculation valves. Proper diagnosis and repair of these components are essential for ensuring that a vehicle meets environmental regulations and operates efficiently. This lesson will cover the key components of emission control systems, teach diagnostic techniques for emission-related problems, and explain the function and maintenance of systems like catalytic converters and exhaust systems. Diagnosing emission-related problems. Vehicles equipped with emission control systems are required to meet specific environmental standards. Diagnosing emission-related problems involves identifying symptoms such as high emissions, poor engine performance, or the illumination of the check engine light, which is often triggered by issues within the emission system. Symptoms of emission system problems. Check engine light symptoms. The CEL may illuminate due to problems with emission components, such as the oxygen sensors, catalytic converter, or EGR valve. Diagnosis. Use an OBD2 scanner to read the diagnostic trouble codes related to emission components. Common codes include P0420 and P0135. Poor engine performance. Symptoms: reduced power, poor acceleration, rough idling, and poor fuel economy can indicate problems with the emission system, particularly the air-fuel ratio. Diagnosis. Check the fuel system, oxygen sensors, and mass airflow sensor to ensure proper fuel delivery and air-fuel mixture. High emissions symptoms. Vehicles with high emissions can fail emissions tests, indicating that the catalytic converter or oxygen sensors are not functioning properly. Diagnosis. Measure the levels of carbon monoxide, hydrocarbons, and nitrogen oxides in the exhaust. A failed emission test points to a malfunctioning emission control component. Common causes of emission-related problems. Faulty oxygen sensors. Symptoms: high or low fuel economy, poor engine performance, or a rough idle. Diagnosis. Test the oxygen sensors using a multimeter or scan tool to measure their output. Sensors with slow response times or incorrect voltage readings should be replaced. Clogged or damaged catalytic converter. Symptoms: poor acceleration, engine misfires, or a noticeable decrease in power. Diagnosis. Use an infrared thermometer to check the temperature differential across the catalytic converter. A cold converter or uneven temperature distribution indicates a clog. Malfunctioning EGR valve. Symptoms: engine knocking, rough idle, or poor fuel efficiency. Diagnosis. Inspect the EGR valve for carbon buildup or faulty solenoids. Use a vacuum pump to test EGR valve operation and clean or replace as necessary. Understanding catalytic converters and exhaust systems. The catalytic converter and exhaust system play critical roles in reducing harmful emissions by transforming harmful gases into less harmful substances. Catalytic converters. The catalytic converter is an emissions control device that reduces harmful pollutants in the engine exhaust, including carbon monoxide, hydrocarbons, and nitrogen oxides. How it works. The catalytic converter contains a ceramic substrate coated with precious metals. These metals act as catalysts to facilitate chemical reactions that transform harmful exhaust gases into harmless substances. CO is converted to CO2. HC is converted to H2O and CO2. NOx is converted to N2 and O2. Common catalytic converter problems. Clogged or blocked converter. Symptoms: reduced engine performance, poor acceleration, and an illuminated check engine light. Diagnosis. Check the temperature of the catalytic converter using an infrared thermometer. A temperature difference between the inlet and outlet of the converter indicates a blockage. Excessive emissions. Symptoms: a failing catalytic converter may result in high levels of NOx and HC during emissions testing. Diagnosis. Use an exhaust gas analyzer to measure the levels of emissions coming from the exhaust. High readings of NOx and HC suggest a problem with the catalytic converter. Exhaust system overview. The exhaust system channels exhaust gases from the engine out of the vehicle through a series of pipes, mufflers, and converters. The key components of the exhaust system include: exhaust manifold collects exhaust gases from the engine cylinders and directs them to the rest of the exhaust system. Oxygen sensors measure the amount of oxygen in the exhaust gases to adjust the air-fuel ratio. Muffler reduces noise created by the engine's exhaust gases. Exhaust pipes direct exhaust gases from the engine to the rear of the vehicle. Diagnosing exhaust system issues. Excessive exhaust noise. Symptoms: loud or abnormal noises coming from the exhaust system. Diagnosis: Inspect for holes, rust, or cracks in the exhaust pipes or muffler. Use a smoke machine to identify leaks in the exhaust system. Exhaust gas leaks. Symptoms: a noticeable exhaust smell inside the cabin, or low performance due to exhaust gas leakage. Diagnosis: inspect the exhaust pipes and joints for any leaks. You may also use a smoke test to detect small leaks. Diagnostic tools for emission control systems. Using the proper diagnostic tools is essential to correctly identify emission-related issues. Here are some of the tools commonly used to diagnose problems in the emission system. OBD2 scanner. An OBD2 scanner is crucial for reading diagnostic trouble codes and understanding the status of emission components. How to use: plug the OBD2 scanner into the vehicle's diagnostic port. Retrieve stored DTCs related to the oxygen sensors, catalytic converter, or EGR system. Analyze the codes to pinpoint which component or system is malfunctioning. Exhaust gas analyzer. An exhaust gas analyzer measures the levels of pollutants in the exhaust, such as CO, HC, and NOx. How to use: connect the exhaust gas analyzer to the exhaust pipe. Measure the emissions produced by the engine during idle and acceleration. Compare the measurements to standard emission levels to identify abnormal readings. Infrared thermometer. An infrared thermometer is used to measure the temperature difference across the catalytic converter. How to use: point the infrared thermometer at the inlet and outlet of the catalytic converter. A temperature differential indicates whether the catalytic converter is operating effectively or is blocked. Summary of emission control system diagnosis. Here's a table showing the emission control system components, including their function, common issues, and diagnostic tools you can use to diagnose issues. You can pause the video if you want more time to review the table. Conclusion and recap. In this lesson, we covered the key components of emission control systems, including catalytic converters, oxygen sensors, and exhaust systems, and learned how to diagnose common issues, such as high emissions and poor performance. We also explored how to use diagnostic tools like OBD2 scanners, exhaust gas analyzers, and infrared thermometers to analyze and repair these systems. Final review and exam day preparation. This lesson is designed to give learners a comprehensive final review before taking the ASE certification test. It will revisit all of the major topics covered throughout the course, from engine repair and diagnosis to HVAC systems and electrical components. In addition, we will review essential troubleshooting techniques that will help students diagnose and resolve vehicle issues during both the exam and in real-world applications. A strong grasp of these key concepts is critical to excelling on the ASE certification test and succeeding as an automotive technician. Introduction to ASE Certification. Before diving into the technical material, it's important to understand the ASE certification process itself and its significance in the automotive industry. What is ASE certification? ASE stands for the National Institute for Automotive Service Excellence, which is an independent organization that provides certification for automotive technicians. Why ASE certification matters. Certification is a recognized industry standard that demonstrates a technician's competence and expertise in automotive repair and service. ASE test structure. The ASE certification test consists of multiple-choice questions covering a wide range of technical topics and requires a practical understanding of each system within the vehicle. Overview of ASE certification test. The test consists of questions on engine performance, transmissions, brakes, HVAC systems, and other key vehicle systems. The goal of the exam is to test both theoretical knowledge and practical application. You must understand the operation of systems, diagnostic procedures, and repair techniques. Engine repair and diagnosis, A1. Engine repair and diagnosis is central to many automotive repairs. Diagnosing engine issues accurately is the first step to providing effective solutions. Key concepts: common engine problems, misfires, poor fuel economy, overheating, rough idling, and exhaust problems. Diagnostic tools: OBD2 scanner, compression tester, fuel pressure gauge, and multimeter are essential for troubleshooting engine issues. Symptoms of engine issues. Look for indicators such as a check engine light, CEL, unusual engine sounds, poor performance, or emissions failures. Troubleshooting techniques. Use OBD2 codes to identify which system or component is malfunctioning. Perform a compression test to assess cylinder health. Test the fuel system and ignition system for functionality and efficiency. Automatic transmissions and transaxles. A2. Automatic transmissions and transaxles are complex systems that require precise control for smooth operation. Key concepts. Components. Torque converters, clutches, planetary gears, and fluid systems. Common problems: slipping gears, delayed shifting or no shifting. Transmission diagnosis. Use transmission fluid pressure gauges, check for leaks, and ensure the proper functioning of the shift solenoids and valve body. Troubleshooting techniques. Perform a fluid level check and assess fluid condition for contamination. Use pressure testing to determine hydraulic system issues. Manual drivetrains and axles. A3. Manual transmission and drivetrain systems are simpler than automatics, but still require attention to detail for optimal performance. Key concepts. Manual transmission components. Clutch, flywheel, gears, and synchronizers. Common problems: hard shifting, clutch slippage, or no engagement. Axle diagnosis. Look for worn CV joints, axle seals, and differential issues. Troubleshooting techniques. Inspect the clutch master cylinder and slave cylinder for leaks. Perform a road test to diagnose issues with the shifting mechanism or differential noise. Suspension and steering. A4. A smooth, safe ride depends on a properly functioning suspension and steering system. These systems work together to ensure control and comfort. Key concepts. Suspension components. Springs, shock absorbers, struts, control arms, and bushings. Steering components. Rack and pinion, steering column, power steering pump, and fluid. Common problems: uneven tire wear, poor handling, steering play, or noise. Troubleshooting techniques. Perform a visual inspection of suspension components for wear, leaks, or damage. Test steering responsiveness and inspect the power steering fluid for proper levels and leaks. Brakes. A5. Brakes are critical for vehicle safety. Proper braking performance relies on the integrity of several key components. Key concepts. Brake system components: brake pads, rotors, calipers, master cylinder, and brake fluid. Common problems: squeaking, grinding, soft pedal feel, or uneven braking. Brake diagnosis. Use brake fluid testers, check for leaks, and inspect pads and rotors for wear. Troubleshooting techniques. Check brake fluid levels and inspect brake lines for leaks. Test brake pressure and perform visual checks of the rotors and pads for wear or damage. Electronic systems. A6. Electrical systems power nearly every modern vehicle component. Understanding these systems is essential for diagnosis and repair. Key concepts. Electrical system components: alternators, batteries, wiring, and fuses. Common problems: no start, dim lights, or intermittent electrical failures. Diagnostic tools. Use a multimeter to measure voltage, resistance, and current. Troubleshooting techniques. Inspect battery voltage and charging system output. Use a voltmeter to test for power to various components. Check fuses, relays, and wiring for continuity. Heating and air conditioning. A7. HVAC systems regulate the temperature and air quality inside a vehicle. Proper diagnosis and repair of these systems is essential. Key concepts. HVAC components: compressor, condenser, evaporator, and blower motor. Common problems: no cooling, weak airflow, or strange odors. Refrigerant types. Understand the difference between R134A and R1234 refrigerants. Troubleshooting techniques. Inspect refrigerant levels and check for leaks. Test blower motor and compressor operation. Use an IR thermometer to measure temperature across the evaporator coil. Engine performance. A8. Engine performance diagnostics are key to understanding how various systems impact a vehicle's power and fuel efficiency. Key concepts: fuel injection and ignition systems. Proper fuel-air mixtures and ignition timing are critical for performance. Common problems: misfires, poor acceleration, and stalling. Diagnostic tools: use OBD2 scanners, fuel pressure gauges, and compression testers. Troubleshooting techniques: check fuel injector function and spark plug operation. Test compression and fuel pressure. Use an OBD2 scanner to detect trouble codes related to performance. Conclusion and recap. In this lesson, we covered a thorough review of the key concepts from all major topics on the ASE certification test, including engine repair, transmissions, brakes, electrical systems, and more. We also reviewed troubleshooting techniques to help you diagnose and repair common vehicle problems. You are now prepared and confident to take the ASE certification test. Test-taking strategies. The ASE certification test is a crucial step for automotive technicians looking to demonstrate their expertise. However, even the most knowledgeable candidates can struggle during the test if they are unprepared in terms of strategy. This lesson focuses on test-taking strategies that will help you manage your time, answer questions effectively, and deal with any test anxiety you may experience. By mastering these strategies, you will approach the ASE exam with confidence and a clear plan for success. Time management. Proper time management is essential to ensure you can complete the entire ASE certification test without feeling rushed or stressed. Understanding the test format. The ASE certification test typically consists of multiple-choice questions, often divided into several sections, based on topics like engine diagnostics, transmissions, brakes, and electrical systems. Here's what to keep in mind. Total questions. Expect around 50 to 100 questions, depending on the specific test. Time limit. You'll generally have 2 to 3 hours to complete the test, so pacing is important. Strategies for effective time management. Read the instructions carefully. Take a few moments at the beginning to read through any instructions and understand the structure of the test. This will save time in the long run. Estimate time per question. If you have 100 questions in 2 hours, that gives you approximately 1 minute per question. Keep an eye on the clock and try to stick to this pace. Skip and return. If you come across a question that's too difficult, skip it and move on. Mark the question for later and come back to it if time allows. Focus on the easy questions first. Start by answering the questions you are confident about. This will help build momentum and reduce anxiety. Don't get stuck on one question. If you don't know the answer to a question after a brief moment of thought, move on. Spending too much time on a single question can waste time that you could spend answering easier questions. Keep track of time. Periodically check the time to ensure you're staying on track. If you're falling behind, adjust your pace. Answering strategies. Different types of questions on the ASE certification test require different strategies. Let's break down the best approach for multiple-choice and scenario-based questions. Multiple-choice questions. Multiple-choice questions are straightforward but can sometimes trick you with closely related answers. Here are some strategies for these questions. Eliminate obvious, incorrect answers. Cross out answers you know are wrong. This will increase your chances of guessing correctly if you're unsure. Look for keywords. Pay attention to keywords in the question and the answer choices. Words like always, never, or most can be clues about the correctness of an answer. Use the process of elimination. If you're unsure of the answer, try eliminating 2 answers that are clearly incorrect. This leaves you with a better chance of guessing the correct answer. Don't overthink. Trust your first instinct on most questions. Often, your initial thought will be the correct one. Scenario-based questions. Scenario-based questions provide real-world situations and ask you to apply your knowledge. These can be trickier as they require problem-solving and critical thinking. Identify the key problem. In each scenario, pinpoint the central issue being presented. What is the primary concern or malfunction? Consider all possible solutions. Scenario questions typically provide multiple possible answers. Consider which option best solves the problem based on your understanding of the system. Look for clues in the wording. Words like first, most likely, or best are important in scenario-based questions. They indicate the most appropriate answer based on the context. Apply what you know. In these questions, always rely on the technical knowledge you've gained during your studies and the practical skills you've developed. Dealing with test anxiety. It's normal to feel anxious before or during a high-stakes exam like the ASE certification test. However, managing your anxiety will help you perform better on the test. Recognizing test anxiety. Test anxiety can manifest in many ways, including racing thoughts, difficulty concentrating, physical symptoms like sweating or a rapid heartbeat. Feeling overwhelmed by the test material. Here are some techniques to manage anxiety. Breathe deeply. If you start feeling anxious during the exam, take a moment to breathe deeply. Deep breathing calms the nervous system and helps to clear your mind. Positive visualization. Before the exam, spend a few minutes visualizing yourself successfully completing the test. This mental exercise can help calm nerves and boost your confidence. Stay positive. Focus on the positive aspects of your preparation. Remind yourself of all the hard work you've put into studying. Take breaks. If the test allows for breaks, use them wisely. Stand up, stretch, and take a few deep breaths to relax your body and clear your mind. Avoid negative thinking. If you encounter a tough question, avoid thinking, "I don't know this." Instead, focus on using your problem-solving skills to work through the question. Stay hydrated and rested. Ensure you get a good night's sleep before the exam and stay hydrated. A rested, well-hydrated mind performs much better under stress. Here are final tips for success. Stay calm and confident. Trust in your preparation. You've studied and practiced, and now it's time to show what you know. Don't rush. Take your time, but keep an eye on the clock to ensure you have enough time to complete all questions. Answer every question. There is no penalty for guessing on multiple-choice questions, so if you don't know the answer, make an educated guess. Summary and recap. In this lesson, we explored effective test-taking strategies for the ASE certification test. Key strategies include time management, answering techniques, and handling test anxiety. By applying these strategies, you can approach the exam with confidence and improve your chances of success. What to expect on exam day. The day of the ASE certification test is an important milestone for automotive technicians. Being well prepared for exam day, knowing what to expect, and managing your time and anxiety effectively can help ensure your success. This lesson provides essential information about what to bring to the test, instructions for taking the ASE test, and tips for staying calm throughout the exam process. Proper preparation will set you up for a smooth, stress-free test-taking experience. What to bring. To ensure a smooth exam day experience, it's crucial to come prepared. Here's a checklist of what you need to bring with you to the test center. Required items. Valid, government-issued ID. This is essential for verification. Acceptable forms of ID include driver's license, passport, state-issued ID card, military ID. Confirmation notice. You will receive a confirmation notice from ASE when you register for the test. Make sure to bring a printed copy or have it accessible on your mobile device. Payment receipt. If you've paid for the exam online or through a payment portal, make sure to bring the payment confirmation. This may be required for check-in. Optional items. Calculator. For some tests, you might need a calculator. Most centers provide basic calculators, but check with your testing center to see if you need to bring your own. Comfortable clothing. You will be sitting for a few hours, so wearing comfortable clothes is important. Dress in layers to accommodate temperature variations in the testing room. Snacks and water. Although food and drink are not typically allowed inside the testing room, it's a good idea to have a light snack or water with you for before or after the test. Some centers may allow you to keep water at your desk, so confirm this with the testing center. Instructions for taking the ASE test. Understanding the check-in process and test-taking instructions is crucial for minimizing stress and ensuring a smooth exam experience. Check-in process, arrival time. Arrive at least 30 minutes before your scheduled test time. This will give you time to check in, get comfortable, and settle in for the exam. ID and confirmation. You will need to show your valid ID and confirmation notice upon arrival at the testing center. The staff will verify your identity and check that you are registered for the test. Test center rules. You will be asked to leave personal belongings like bags, cell phones, and study materials outside the testing room. Some centers will provide lockers for your personal items. Test format and rules. Test duration. The ASE certification test typically lasts between 2 to 3 hours, depending on the specific exam you are taking. Make sure to pace yourself so that you have enough time to complete all sections. Number of questions. The test consists of around 50 to 100 questions, depending on the specific ASE certification. Most questions are multiple choice or scenario-based. Test environment. You will be given a computer-based test with a user-friendly interface that allows you to navigate between questions, flag questions for later review, and skip questions you may want to return to. Breaks. Depending on the exam's duration, some centers may allow short breaks. If you need to take a break, raise your hand and ask the proctor for permission. Typically, you are allowed to take a break for things like using the restroom. No cheating. The test center will strictly enforce rules against cheating. If you are caught using unauthorized materials, you will be disqualified from the exam. Tips for staying calm. Test anxiety is a common experience, but managing it effectively will help you perform your best. Here are some strategies for staying calm and focused during the test. Before the test, preparation. Get enough sleep. Ensure that you get 7 to 8 hours of sleep the night before the exam. Being well rested will help you stay focused during the test. Eat a healthy meal. Have a balanced meal before the test. Avoid heavy, greasy foods that can make you feel sluggish. Opt for something with protein and complex carbs to sustain your energy. Visualize success. Take a few minutes to visualize yourself confidently completing the test. Imagine going through the questions smoothly and answering them correctly. Positive visualization is a proven technique to reduce anxiety and boost confidence. Arrive early. Arriving early at the testing center gives you time to relax, get accustomed to the environment, and settle your nerves before starting. During the test, staying calm. Breathe deeply. If you start feeling overwhelmed, take a few deep breaths. This will help calm your nervous system and refocus your mind. Stay positive. If you encounter a difficult question, stay positive and focus on the solutions. Remind yourself that you've studied and are well prepared for the exam. Pace yourself. Keep track of time, but don't rush. Work at a comfortable pace, and remember, you can always return to skipped questions later. Take short mental breaks. If you feel your focus slipping, take a second to close your eyes, breathe, and reset for a moment. This can help reduce mental fatigue and anxiety. After the test, relax and reflect. Once the test is over, take a few moments to relax. You've completed the process. The important thing is to stay calm, regardless of how you think you performed. Remember, the ASE test is just one step in your career, and you can always retake the test if needed. Final tips for exam day success. Stay hydrated. Bring a water bottle, if allowed, and keep yourself hydrated to maintain focus. Stay organized. Double-check your materials before leaving home to ensure you don't forget anything important. Trust your preparation. Remember that you've prepared for this moment. Trust in your study routine and problem-solving skills. Summary and recap. In this lesson, we reviewed what to expect on ASE exam day. Key takeaways include knowing what to bring, understanding the check-in process, and following test-taking instructions. We also covered practical strategies for staying calm and managing anxiety during the test, which are essential for performing well. With the tips and preparation provided, you are now ready to approach the ASE certification test with confidence.